Go for it.
Cool.
I'm going to make myself the spotlight for a moment. Right, welcome back then, everyone, to the second session of the second Reddit Robotics Showcase. We hope you're having a good time and enjoy the couple of hours off, hopefully to get some blood into your legs before we now sit down to enjoy more PowerPoint presentations. And we're kicking off with mobile robots in the wild, courtesy of Professor Marc Hanheide from the Lincoln Center for Autonomous Systems. I should have guessed systems, but the thing was in the way. So I'll hand over to you now. Thank you, Marc.
Yeah, brilliant. Thank you very much, Oliver. And welcome, everybody. And good evening for those in the UK and whatever. Is it afternoon? Just after lunch for the ones in the US and all over the world. So, yeah, I was invited very spontaneously to step in and talk a little bit about mobile robots, and I like to talk about robots in the wild. I'm going to tell you a little bit more about what that means for me. Hopefully it's going to take about 40 minutes or so, and we should have time to discuss some things, because I'm going to give you quite a broad brush of different systems, projects, domains of mobile robots that I've been playing with over the years. And so it's not going to be particularly deep, but if you've got any follow-up questions, ask me later on. And this is also not going to be overloaded with formulas. I probably got like one or so just to blind you all, but it's pretty much hopefully easily digestible for everyone. Right, so moving forward, when I say robots in the wild, I don't mean like cute robots in the jungles necessarily. So it's not really this, even though we're going to talk a lot about outdoor robotics as well as we move on. I'm also not talking about these types of things, and I had to put a little video on from Ocado just because we had that session earlier on. And we're not talking about these sort of fantastic robots that they have shown, right? Where we've seen these robots roaming about in their hives or whatever it may be, although it's called. No. That's not what I mean with robots in the wild. This is really nice environments for robots, as is the one on the left. So I'm really talking about some of the challenges that come when you've got robots out in schools, or you may have them out in the general public. So this is not all just my projects here, but just an indication of some other projects here where they've got one robot in, I think this was in Munich, where the robot had to find its way from one place to another. Quite fascinating work there. And the kind of overall ambition is robots leaving the cages of whatever controlled environment, be going into the wilderness, and I would even say the hostility of human habitats, of the world we made for us humans, and we clearly did not make for humans. And then it's about mobile robots, so it's all about how they can move about, how they can adapt to these environments, and how they can actually still be useful. So with that just introduction, I'm going to give a very brief overview of the center that I'm in. So I'm the director of this Center for Autonomous Systems at the University of Lincoln. As you see, we cover quite a far range with a lot of people. So this is the picture from our last away day, with lots of folks working on all sorts of areas of robotics. And you see on the left-hand side also the sort of main domains that we are working in. And these bubbles are roughly corresponding to the amount of projects, papers, funding that goes into those different domains, if you want, with agri-food being a very particular big one. But we're touching on quite a number of them, and I'm going to give you a bit of a sweep through some of those projects that we are interested in all around the area of mobile robots. And in this fascinating network diagram on the right, you will see, if you go to our website, also at the bottom, you can actually see a more interactive version of that. You see that is a lot of people working on mobile robotics. My own personal view, and this is a slide I've been using for a very long time now, is this vision of eventually you will be able to buy your own service robot. You can already buy robots, but it's one that is really just almost equipped with all sorts of just innate capabilities. We don't want to do developmental robotics. We don't want to have robots that you teach everything from scratch, right? You wouldn't be prepared to almost raise another child to eventually have a robot that makes you a cup of tea. But so they come up with some competences, but they have not seen your specific environment. They have not been in your home. They have not been in your field. They may not have been in your warehouse. They may not have been in your hospital. So they need to come with a certain level of adaptation so that they can actually make sense of the world and operate in an environment that they haven't known before. And that, of course, relates to a large extent to all sorts of mapping exercises, if you want, when it comes to mobile robots. What I'm particularly excited about is taking robots out into the real world and then having them running on their own, doing their job on their own, which requires a large degree of reliability, and which is also why I have to my name often the tag of long-term autonomy, right? So we were trying to actually make robots that are able to run on their own, do their jobs, and ideally even get better on the job. So I'll come back to this overall theme of getting better on the job as we go along. And this is a massive, massive multidisciplinary exercise. So we're really building large-scale robotic systems that have aspects of machine learning, control engineering, AI. Why is the machine learning twice? Interesting, because it's very important, particularly also human-robot interaction, networking, Internet of Things, embedding them into smart environments, etc. So it comes with all these different aspects, trying to put them together to solve certain problems, right? So that's so far the kind of biggest scope of what we're trying with robotics. Now, enough of the wishy-washy general bit. Let's look at some specific projects. And here's our first project. This is the robot Linda. This is from a European project that ended about 2-3 years ago now. This was one of the applications of these robots was that it was deployed in a care scenario, in a care home, actually in Austria. You see this on the right-hand side. This is the cycle that almost defines a lot of the research I'm interested in doing, right? We may have robust, intelligent, autonomous behaviors, which allow us to have long run times. That being deployed in an environment running for a long period of time allows us to learn about what the environment looks like, and we could probably identify novel things we can learn about this. So then we exploit what we have learned. We try to get better behaviors, getting better on the job. And as a result, we get more robust, better behavior, which allows us to stay longer and blah, 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 right? So we get these robots basically on their own and hopefully improving the way they deliver whatever services it will be. And this was in a particular simple scenario of a care home. When I say simple, I don't mean necessarily that it's just simple to have a robot in a care home, but we have actually just focused on a quite simple task. I'll come to that in a second. This is just to give you an indication of what the challenge is, right? This was a robot down in Vienna. It's called Haus der Barmherzigkeit, and I'm up there in Lincoln. You see that on the left, top left of the map. And obviously, we dropped it off there. We started it all off, and then it was there for a total of a year, delivering services in the care home. We had a lot of, web-based remote management. Those who know ROS may know this, the kind of web services of ROS that we used extensively to make really nicely websites. We had some clients that connected to Slack and then later on to Teams that automatically allowed the robot to ping us when there was something going wrong. I'm going to show you a couple of things that go wrong later on when you leave a robot on its own. And so that was kind of an infrastructure that we still use today when we put robots out into the real world and leave them alone, but we still need to somehow have some sort of control over them, and eventually, once in a while, have to check how they're doing. Now, this robot in this care home did a number of things. It was a bell bot, so it could take visitors around and guide them to their respective places, maybe offices or therapy places, etc. It also was part of a working group, a really exciting new way of using mobile robots, because indeed this robot was in this working group a pace setter. So it basically joined a group of elderly residents that have had quite some cognitive challenges. So they often forgot what they were currently engaged in. And the robot was there to provide a sort of focal point and guide them on a walking tour. I can't show you many videos of that. So that's why I, for data protection reasons. So I'm not going to show you much about that, but it's just another interesting task for mobile robots once you have them reliable enough to actually let them roam freely with people around them. I'm going to talk a bit more about what's called the info terminal, and that sounds quite boring because it's basically an information display as you see it here on wheels, right? It's this robot. It can move around. It can find people to interact with them, offer its services. And the really interesting question for us was, how can we deliver services at the right place at the right time? So when you've got moving robots, whatever services they provide, the question is always, if they have a large environment, where should they be at what time? And of course, you can program this all in. But as I said, what we really wanted to do is get better on the job. So starting off with some basic standard roaming behavior, it would roam this care home and say like, oh, look, here I am. You can use me if you want for getting some information about menus and what's going on, weather, news, etc. But we wanted to get, we didn't know where it should be. And so we wanted to actually have it adapt over time to these places. And one of the underpinning algorithmic work, AI work, was, or the sort of main hypothesis was that our world as humans is clearly not static, right? We are all moving about, we're all doing all sorts of things, but humans are creatures of routines. We have a lot of routine behavior, be it being awake, falling asleep, be it having regular food, be it doing certain hygiene tasks in the morning or in the evening. So a lot of the stuff we do is quite repetitive. And in particular, if you're in a care home, that's probably an environment that is characterized by quite a clear routine. And rather than programming in this routine, we wanted to discover it, right? So we wanted to have some AI methodology that allowed us to discover it. So here's a map. This is the sort of map of the overall environment. Oops, sorry. And overall, this is the largest care home in Austria. And the question really for us was, we wanted to see where is the robot when. We know this, we can record this, right? We have localization of the robot, and we, of course, have the time. And did people use it? So that's the question. So we've got a simple thing where we have a location, we've got a time, and we have a certain probability of people using it potentially. And with that information, we tried to learn this. And we have done this over a long period of time. And what you then can do is a method that we had created that is called Fremont Frequency Map Enhancement, which is quite simple as a spectrum of events or a spectrum of occurrences, right? So we're modeling this probability of having success, having actually interaction with somebody, being useful. We're modeling that not as just a probability overall, or not even just at a specific place. We're doing it as a spectrum over time, assuming that it is more useful at some places at some times and less useful in others. So we have a periodic probability function, basically. And what you actually do, and you can learn this. So basically, for those who have some background in engineering in particular and know about signals, this is basically a Fourier transform. And what you can then do is try to use all the data that you have when you're there, and a successful click is done, like people actually use the robot. You record this, and then you can try to guess the most likely, the most dominant frequency components in there. And you can model that and give you an idea of where the robot should go at a certain time, because it is most likely to get some customers, right? So it's all about modeling customers, if you want. And this is a nice map of the results. So the first sort of set of results we've got here with some quite obvious findings. So one interesting bit is, if you look at the lifts, the elevators in your care home, they seem to be a quite important place to go. And that is probably because people are just opportunistic while waiting for the lift, and there's a robot there, they're going to use it. It's also interesting when you see down here a very unsuccessful place. That was actually a place that was in the, that initially was more likely to get some successes, but due to some rearrangements over this time, in this care home, people put a plant there, and it was almost impossible to reach the robot there. So over the time, it had learned that it is not a good place, and eventually then frequented it less often. Also interesting, kindergarten, no surprise there. That has the highest clicks per interaction. So lots of interaction when you've got kids around. They love it, right? And they love robots, and immediately that is a successful spot to be, because in this care home, they had a had a kindergarten embedded into it, mainly for staff. And interestingly, of course, that one is only open to certain hours. And indeed, our model had learned that it only makes sense to go to the kindergarten while it is open. And we had never programmed this, and it would not go there anymore after it had closed, because there was hardly anyone there. And it's exactly this sort of thing that you can learn on the way. And if you do this, and you can deploy the system, continuously update the information that you receive about these successes and modeling this with these frequencies, you can see that we get a nice upward trend. I don't know how much you know about the novelty factor in robotics. The usual curves when you deploy a robot into an environment and you measure how much people interact with it, the usual one looks like this. Right? People love it initially. Oh, it's something new. They try it out. If it's not particularly useful, they will stop using it. Right? And you get fewer and fewer interactions. So for us to be able to beat this trend, let's say, right, where we saw that people were continuously using it more, was quite something for us, because it showed us that we actually got better on the job. And it's all about determining in a map where you want to be to offer your services. So, because one of the key things for mobile robots, obviously, is that they can change their position and can actually learn, as that's what we've shown here, that it can learn where they are most useful, even if the task is a fairly simple one. So that was quite an encouraging result. We've deployed the same robot also in office buildings. This was in the Transport Systems Catapult in Milton Keynes in the UK. And I wanted to just show you that, to have a bit of a reflection on competence and reliability of robots as well. Again, similar setting, robot was there. Task was a bit different, so it had some environmental monitoring tasks, etc. But the main task was, again, roam around the building, go to the right places at the right time, etc. But there were some challenges. And I want to talk about some of these challenges. And one of these challenges for mobile robots in our environments are doors. So here's one, and we had implemented an interesting, a simple, straightforward behavior of using speech, of asking any humans that would probably walk by to hold the door open for us. And then it would go through it autonomously. But sometimes, of course, it would also stand there for a long while and would wait for somebody to appear. And of course, eventually people also get a little bit frustrated about some of it, because if it was on continuously going to the same routes, it could start annoying the people that had, unfortunately, their desks nearby. And it was always asking, oh, can you please open the door for me? Can you please open the door for me? But this robot didn't have arms. People perfectly understood it cannot open doors. Of course, we could change the environment. We could make some electric doors in there, and we could hook them up with some IoT stuff. And that's what we've done in other scenarios where they have to be deployed for a long period of time. But here you can actually use humans to help. So if the competence of the robot isn't quite good enough and you are in human environments, you can ask humans to help you out. And that's quite cool. And people are very willing to help out, is what we found from this. And they're very understanding to this. What they are less understanding about is what I called unacceptable incompetence. And this is just the map from the cam you've seen earlier. And the purple dots on here are is a map of all the navigation problems we have encountered. And the robot was not able to move from the place it was at to the place it wanted to go. Various reasons for that: localization failing, navigation, like, seeing some obstacles that were more or less ghosts, something that, it just had populated the map with obstacles and it didn't quite know how to get out of this. And this behavior was similar. People would be asked, if somebody were around, oh, can you just push me a little bit out of this misery, because I don't know how to get out of this myself. So, human populated provides an opportunity there. However, it's, of course, if you have a robot and it gets stuck in the same place again and again and again, people are going to hate you very quickly. So that's why we started off looking at, well, we really should make use of these demonstrations that people give us, right? If we're stuck and somebody comes along, is kind enough to us to show how we can wiggle out of this situation, push us along in the right direction again, we really should make use of this, because it clearly was a way of getting away from this. So instead of just ending up in the same misery again and again, what we tried is to learn these behaviors that people demonstrated, right? See if you have a local navigation behavior, because that's what people are demonstrating, if you can replay it depending on the context you're at. And this is quite important, because indeed the statistics that we've got in here, and you see this is when you see this edge number, you see that most of the failures happen in always the same place, because it's somewhat a challenging, very narrow place where the robot gets stuck. And if we can learn how to get out of these situations overall, if it's just like the first 10 or 20 of these problems, we're going to cover 90% of the navigation challenges that the robot may have in this environment. And indeed, people don't help very often because this is not a very populous environment. So very often the robot just stands there and desperately waits for somebody to help it out. And just quick, very brief technical excursion here. We use what is called Gaussian processes to basically learn the sort of mean trajectory with some variance and be able to also classify situations based on the sensor readings the robot to identify, oh, this may be one of these situations that we have seen before. And if we have this, then we can play back basically one of those learned Gaussian processes to avoid getting stuck in there again. Here, so on the top right, you see this simple behavior of a robot where it has detected that, oh yeah, it's too narrow, it can't go through this, so it got stuck. But then it could actually take one of these previously trained examples to continue, and basically after just 2 meters of replaying a trained trajectory, it can carry on. So that's a way to make robots more acceptable, because you don't ask for the same solution again and again, and you don't annoy people. And at the same time, of course, it increases the reliability and the overall autonomy of a system that can do its job properly, again, without modeling each situation directly, just using the demonstrations from people as they are available. Cool. So that was a little bit in care and a little bit in offices. I had to put this in again in reference to the earlier keynote from Ocado, that we also do some human-centered robotics in logistics. And the main difference here is, again, we're not talking about environments, warehouses that are really made for robots. We're talking here about robots being run in warehouses that are were initially designed without any automation in scope. So this is just floors with like pallets stuck here and some shelving stuff at another place, which actually exist a lot if you're not one of the big players of like Amazon or Ocado and so on, right? So we're trying to give an early and easy entry route for businesses that cannot just chuck their old warehouse logistics solution out and move on to a custom-built, roboticized 100 million warehouse solution, one where they can actually introduce robots into the existing environment. So that's the sort of main idea of this also European project. And that comes, you need to deal with a lot of different things. In particular, you want to, again, capture how does the world change during the day. So for instance, there will be, again, typical routines. People go for lunch and stop working, then they come back, and you can already predict where they will likely be. You have your list of orders, so you know what sort of will likely happen. You can link this up with the warehouse management system, but we don't want to have the standard guided vehicles, right? We want to have the flexibility of doing path planning and giving the warehouse also the option to just drop a pallet here, right? They have a mixed fleet of human operated machines and autonomously operated machines. This is something that we've trialed here in what is the National Center for Food Manufacturing. So this is some navigation there. Again, you don't see any tracks. This is all based on maps, mainly based on LiDAR-based maps. You see a lot of LiDARs flickering around here. Quite vast open spaces in this particular part of the the warehouse. And the main challenge that we've been focusing on was to do something called human-aware navigation. And if you guys have been toying with obstacle avoidance in robots, you are aware that there is many good solutions that take a robot from place A to place B, and it may encounter some obstacles that it can perceive with its sensors and then plans nice routes around this. And if you're doing ROS, you may even know about like dynamic window approach. This is one of the standard ones you're using. The big challenge, of course, is that humans are a bit different, right? They're dynamic obstacles, and in particular, they are reacting to the robot as well. And in particular, they have usually an intention when they move, right? They may want to get past you, they may want to overtake you, or they actually want to meet you. And we want to embed this sort of intention of the humans into the navigation approach of the robot. Using something that is called QTC, so it's the sort of called the qualitative trajectory calculus, which is qualitative, so not in a quantitative way, of capturing the main motion of people on a 2D plane. Not going to go into too much detail, but for instance, what we can then do data-driven again, show, as we see it here on the right-hand side, there's actually two main paths that we've learned from data. People go past on one side or go past on the other. And they go through various states in that, and you invited to look up QTC to learn a bit more about that. Here's the sort of general principle. And what you then do is, if you recognize a certain situation, you can learn these sort of typical paths that people take in the presence of a robot, and you then constrain which area the robot is allowed to go into. And what the good thing is about that is it gives a certain commitment of the robot. You don't have this situation, as you may all know, you meet in a corridor face to face, and you engage in this kind of almost dance, right? Who goes where? How do we move around each other? There's some kind of cultural conventions, right-hand side, left-hand side traffic, for instance. And we didn't want to model, again, any of this. We wanted to actually learn it from the data, right? How do people move? And then how do we capture the main typical encounters and motions that are happening? And that's exactly what we've been doing here. So we've done this in simulation and in reality. And it basically adjusts the sectors that the robot can move to. And it's committed then, for instance, in this case here, to have something like a right-hand side traffic goal. And that avoids, because very early it already indicates which direction it's going. So that's an area of that we're quite interested in, human-aware navigation, and showing that actually you can increase the safety for people. You can also, at the same time, achieve a better performance for the robots, so they reach the goals quicker if they are committing to certain routes that also take the human intention into account. Okay, you see, it's pretty quick run through. We're moving now from care, offices, logistics, outdoors, right? So we're going into the real world. And as you've seen earlier on, we're doing a lot of work in agriculture, and we're working particularly close with a company called Saga Robotics. And this is one of their robots here, where we've got quite a fleet of those in different form factors to do a variety of tasks on farms. So we've got our own little agricultural campus. So this is actually from the strawberry farm that we are operating ourselves. And we get some very nice fresh fruits almost on a daily basis. And a simple task, the moment you are able to reliably move a robot from one place to another, is to automate not the whole thing. So we have, you may have heard about lots of problems with labor, finding people that are actually willing to pick the crops in our fields. It's actually a real problem, and I don't think there's many robotic solutions outdoor yet for this sort of strawberries or cucumbers, etc., that are really ready for the market yet. We've seen great videos of different picking solutions, and there's really lots of companies making absolutely great progress towards this, but it's not quite there yet to provide the solution that is competing with what humans can do in terms of speed and dexterity. But what you can already do, we know this, we can move stuff about, right? We've got mobile robots and they can do logistics. And indeed, about 20% of the time that people that are picking in these fields, they are spending on transporting. They're picking and then they're moving stuff somewhere else. So we were looking at, can we actually increase the productivity by just automating the transportation of that as the first easy thing? And again, lots of underlying work on making navigation reliable and work properly, because indeed, while in agriculture, everybody uses RTK GPS, the moment you enter polytunnels with metal structures, the precision drops quite significantly. And we also have to then take these crops that we've harvested into buildings. So it's even then GPS doesn't become an option. So we've got a bespoke hybrid solution. So this is the building where we need to drive into. So we've got a hybrid solution of GPS and laser-based navigation that allows us to kind of traverse from indoors to outdoors. And this is a solution that is actually now commercially being used by our partners from Saga Robotics. They run tens of kilometers every night for a specific bespoke UV treatment solution on strawberries. I'm not going to go into the details, but it's you can see, like, when you've been working on robot navigation for quite a while, you can see the route towards commercialization quite quickly from that as well. So a lot of underlying work was to automatically improve navigation parameters and so on. So with that, and I'm going to speed up a little bit. We're going to now see, of course, we need to talk about many robots operating together because farms are huge. You can't just have one single robot serving a gang of 50 people that are picking in the fields. So we need to talk about fleets of robots and need to coordinate them. And with that comes interesting aspects of avoiding deadlocks. You know, you've got a very constrained environment in these fields. So you see these are all the beds where the strawberries are. And you want to have these robots going along here. And of course, they can't go across this way, right? So you can easily see that you're being trapped between a picker and another robot and can't move. So you really must plan the overall fleet and coordinate that. Again, bit reference to what we've heard earlier from Ocado. Again, it's a central coordination system that ensures that the robots go to the right places and they're not being trapped. And so we also need to know where these pickers are, these people are in this environment. I'll come back to that in a second. So just moving forward in this fairly quickly, the system we've got is that the pickers can call robots over. So if they have something that needs to be offloaded, they can push a button and then a robot will be allocated, the one that is best suited for the job at the moment, taking into account battery stand, etc. And then it goes along these topological edges and is assigned to the task. So basically just a classical fleet task assignment problem where humans can just call robots over through either with their phones or bespoke device, as we see. They can also cancel tasks and we do all the kind of traffic resolution. So for instance, here, this part is blocked. So the robot actually has to go all the way around. So there's some route planning in here and deadlock avoiding and also task planning, task scheduling. And then you can, if you have these sort of topological representation that you've just seen, you can take that and go away from all the nitty-gritty bits of how you navigate close around humans, as we've seen before, to just look at the whole farm and look at the whole structure and run what we call discrete event simulations very quickly through. So you can just say, okay, what would the situation be if I would put 10 robots in with 50 people working there? How much will the robots be utilized? How much gain will I get from putting robots there, and is the optimal number something like 10 or 15 or so on, right? So you want to have the right trade-off between how many robots need to support how many pickers, because robots are obviously also expensive. Yeah, and so this is not only by a phone system, as we've seen here. So that's a web app using the GPS on your phone. We have got an embedded system as well that uses some ESP32 with an embedded GPS and 4G communication. So you basically have a little dongle and you can just take it into the field and you push a button and the robot comes to you. Right? That's pretty much what it does. It's quite interesting that indeed these cheap devices cost around 15 quid now. This little embedded system that we've developed, which is just very, very crappy GPS or not very good GPS. We have then, of course, the challenge that the robot must enter the right row where the person actually is. It mustn't go down here. It mustn't go down here. Okay. So that means we have to improve the precision. Right? 3 meters won't be enough. A row is about 1 meter wide. If the GPS, even like getting just 3 meter precision from this type of GPS devices is quite good already. So what can we do? Can we use AI to actually make it better? And this is standard what you would expect robotics localization technology uses as well, right? You may have all heard of something like particle filter. So we're using now the knowledge about the farm so that it has these very long rows and that you cannot cross from here to here, and you cannot cross from here to here, and you cannot cross from here to here. And we put that into what we call a topological particle filter. Oh, here's the formula. So not going to talk much about that. Let's move forward. The idea is that you have an anticipation. You know these pickers, how long they're probably going to stay at one place and when they are going to move forward. So with that model, as a probabilistic model, you can take the very noisy information you're getting in, and over time, because you have a quite strict model of what this data can relate to, you actually are accumulating enough evidence to be able to determine which row the robot should go to. And when you do that, indeed, we can figure that it gets to the right place. And we use the same system, the same sort of coordination system to deploy all sorts of tasks on the farm. Here on the left-hand side, you see one of these UV robots. So it's a robot that uses UVC light to treat against powdery mildew instead of using chemicals. Great impact, right? We don't need any chemicals to fight this fungus anymore on our strawberries. We just use light and run these robots autonomously at nighttime. And you use the same sort of coordinator, you schedule a task, and it will go and does the whole traversal of this particular farm environment. And this is one of the commercial solutions that are built on top of that. Okay, interest of time, we do a lot of stuff in agricultural robotics. We use the same sort of technology to do phenotyping, go out and automatically scan fields for traits of plants. We do soil sampling with these type of robots. So a lot of the moment you have a reliable autonomy stack, you can start building a lot of the additional value tasks around that. And this is like also some demonstration that was at COP26. I want to just spend the last 10 minutes or so on this robot in the museum, mainly run by my fantastic PhD student, Francesco here, which is, again, a mobile robot. And you see it's a similar, as we kind of closing the loop back to the first robot that we've seen. And this one is a tour guide. It goes, it's constantly deployed in the museum, into the Archaeological Museum in Lincoln, and waits for people, similar as we've seen before, to offer tours, right? So you can go there and you can actually book onto different types of tours. And initially, this was just to use the technology we had developed in Strands. We have all this stuff about how we can safely navigate among people and how we not make the same mistakes again, etc. But here we wanted to see, can we take this getting better on the job a step further? So again, about, where should it be? That's all the same bits as you've seen before. But interestingly here, the tours that the robot does, right? It guides people around and tells them about the different artifacts. These tours were crafted by the educational team of the museum. So they gave different themes, death and burial, etc. And had different stations where it should go. And we probably all know when we have a museum tour guide that either it's too long or it's too boring, or they don't tell us the right amount of information, or we would rather stop now. And so we wanted to actually get better on the job by learning and changing the tours. I call this now basically reinforcement learning in the public domain, right? Can we actually learn all the actions that the robot can decide, where it should go, how much it should tell you about each artifact? It's typically a set of actions that the robot can choose from. And we have a state space, we know where we are, we know we can perceive people, etc. So we can hopefully learn in the long term to get better on the job again, right? And choose the right actions, choose the right tour length, etc. And that's what we've tried. And the first interesting question was then, well, I don't know how much you know about reinforcement learning, but reinforcement learning is all about getting some reward, to get some feedback, whether you're doing well or not so well. And what we first did, classic technology of these days, we thought like, oh yeah, let's try to learn some engagement features. So we take a camera, we're looking for people, and can we identify whether they are engaged or not? If you guys have any interest in human-robot interaction, there's lots of very, very developed engagement models out there. They are all properly founded in psychology about establishing gaze and how much you blink, etc. So you could make all sorts of very complicated things here. We wanted to go completely simple. We said like, well, I think humans have a very intuitive understanding of what engagement means. I know if I'm standing in a classroom, I know if people are engaged. I look at them and I can see whether they are kind of starting to doze off or not, whether they're still with me. So we just did machine learning, convolutional neural network, took the video frames, did some LSTM long short-term memories, and basically made what we call a regression onto an interval from 0 to 1. And we showed videos to people, and we just gave them a slider to say like, oh yeah, this looks like people are very engaged. Oh, this looks like they're not so engaged. Well, you've got a lot of data from that. It's fairly quick. People can play these videos very quickly and just kind of assess on a slider if they think that people are engaged or not. You have that trained, and then you put this on a robot, and it gives you some noisy reward, right? And it sees whether people are still with you and are looking at the screen, or rather doing something else, or even walking off. And that you can use as a feedback function for what is called a reinforcement learning. So rather than having to, again, do anything ourselves, we have these robots making its own experiences, just having an understanding whether people are engaged or not. And you see, this is even challenging because the pandemic hit, and initially our engagement model was trained with people without face masks. And then we were quite surprised that it worked fairly all right still when people showed up with face masks. And yeah, then we do some reinforcement learning in this domain. And actually, again, to make it simple, what we vary then is where the robot goes, how much content it provides about each of these artifacts. And then you see that even on the current context, whether people are still engaged or not, it changes the tool. It takes shortcuts. It shortens it if it sees like people are probably tending to doze off, and it even then decides also if they are very engaged, it keeps on describing more. And it has learned this all basically just from being out there and getting these experiences, and it's still running. So if you happen to be at Lincoln, you may well have a look at that. So here's the main results, the main findings we got from that. Important part is this was the expected phase when you don't learn. So we had this robot running for quite a while, and people had less and less interest and basically had less and less success of completing the tour to the end. And then we started actually adjusting the tools through the system I've just described. And over these weeks that we've done that, we've seen the nice trend going up, pretty much the same sort of trend as I've shown you before. So that was very good. PhD student extremely happy because it seemed to have worked, and we really got much more interest from that. And then we did a kind of just control condition again. We turned this whole adaptation off and went back to our original model, and immediately it fell down, and people were not as interested anymore. So we could say from learning on the job, we got better than the tools that the educators provided us first with. Not sure they like the message. But yeah, if you happen to go to IROS this year, then you will find that this is one of the best paper nominations, both for us. Cool. So that brings me pretty much to the end. Just going to give you a few interesting things that happens when you observe mobile robots out in the wild. Biggest problem is emergency stop buttons. You know, they're big red buttons. They have to be. Kids love big red buttons. Not only kids love big red buttons, also other adults do it. And the main intervention we had to do when we had these robots out in the museum or in the care home was to release remotely the emergency button. Because indeed people just pressed it and there was no emergency, but it is just, you know, a red button that is interesting. It's a robot to play with. This, what you see down here, is the sensor stream, laser sensor stream from our robot. And you see it's not aligned with the wall anymore. It is initially, and then something is happening. And of course, we only see this data, right? The robot is 1,000 miles away. We don't know what's happening. We see that this is happening from in the sensor stream, and the robot told us that it cannot localize anymore. What happened is that this part here is the entrance to the chapel and the care home. And we already knew that the priest wasn't a big fan of robots. So we had that in previous conversations. And he didn't like that the robot had learned that on a Sunday morning, being in front of the chapel probably gives you quite a few customers that would like to interact with you. So what did he do? Tilted it and dragged it across the floor just to make it go away. That's what we had found then eventually when we collected all the evidence and had a chat with them. So you need to take these contexts into account, right? You have different users in an environment. And this is the last one here is a video that you may have seen already. This is quite famous from in Japan. Again, what happens when you deploy robots in public spaces? This is in a shopping mall. So again, robots are huge attraction to kids. And what you get to see is then that indeed what is probably considered playful is also very hostile to robots. It's not just priests dragging robots across the floor, right? Playfully playing with the robots, caging it in. It can't do its job anymore because, of course, it cannot move. And then even becomes, this was also a problem we had, that people just kind of grab the sensors and violently move them around and they become decalibrated. And then we have kicking and all sorts of abusive behavior. So that is why I often say that when you go out to the normal world, it is actually a very hostile environment for robots. Right, this was our robot having mopped up a chewing gum from the floor and couldn't charge anymore. So that's when you have to send some engineers in and check, like, oh no, whatever we do, it docks autonomously. It doesn't pick up any power anymore. Chewing gum. And we've had robots falling down the stairs because somebody had disabled the downward-facing cliff detector. Again, human error. You have people changing the environment of staging a Christmas market in the care home or putting a sofa right on where the robot is supposed to deliver its task. Down here, we had a sofa or a chair blocking exactly the charging station. This charging station is right there, right? And it can't reach it. So just the robot calls us and says, oh, help me, can't charge. And it's because people are not aware. Right? We're not used yet to share our environment with humans. So they face a lot of challenges. Okay, I think we only have some time for questions, so I'm going to quickly run through to the final slide. You can study at Lincoln. We do all sorts of stuff, and I need to announce that we have a new BSc in robotics that starts in 2023. Of course, we've got job opportunities that are out there, and I can probably share links later on Reddit or on YouTube if that's useful. And we also have a center for doctoral training. So if you're thinking about doing a PhD, there's also a chance to do that in Agri robotics. Thank you.
Wonderful. That was really, really good. Thank you very much. Gosh, I've got a few questions certainly that I'd like to ask, but I think it's fair to hand over to Michael first, because obviously I'm also in the UK robotics scene, so I think let's get an international perspective on it. Michael.
Absolutely. Yeah, happy to represent America in here. So we're still waiting on questions from the YouTube group, but in the meantime, I have a few of my own that I'd love to ask. Kind of harkening back to at the beginning of your presentation when you were talking about, you know, this kind of intentional mistakes or intentional like things the robot couldn't do with, you know, not being able to open the door and having to kind of ask for help in order to build that trust. You know, have you experienced it at all with kind of gradually making the robot more capable so that it starts out by building that trust and then slowly is able to kind of become more and more capable as a robot at doing its job without breaking down that trust it has with the humans?
So trust is a fickle thing, I have to say. Trust is a very, so we also got one project which is in the UK there's something called Trustworthy Autonomous Systems Hub. It's a big research program, and there's something where we actually study trust in the context of this museum robot. And the biggest problem we had also in the care home was it's very difficult to recover from failure. And so in particular, we had this walking group robot, right, that I referred to, where the robot would take the lead and guide people around in some physical exercise. And that was very popular also with the therapists until one day it didn't work and it just got stuck and it became a burden for them. And they operate on a very tight schedule. And we have done, I haven't got the slides here, but you know, we gave them an assessment after every run, right? So they should say how well did it work, how well was it perceived, much did it help you, etc. And it was really good scores. And then there was this one error mistake that happened, and of course it fell right down there. So that's so far expected. The problem was, all the next runs we considered engineers-wise, they were absolutely perfect again, right? They absolutely worked, nothing wrong with them, but we never reached back to the actual original trust, let's say, right? It slowly crept up. So every time it kind of worked, you saw an increase and people were trusting it more and would probably use it. So it takes a long time to recover from that. And that's why, that's very, very important, I think, when we think about these systems. And people have high expectations with robots principally, then they normally have a very quick realignment about what this system can actually do and what it cannot do, and they're somewhat tolerable and accept that. But then if it really fails, you lose a lot, and that takes a long while to get back, which is why we now often, you know, for instance, we have decided against any speech understanding. We've trialed that, but it led to such large degree of frustration in many of those domains, because there's background noise. People in Austria speak a dialect that not necessarily all German speech understanding systems are particularly good at. that we actually decided, no, it's too risky. Right? We're going to lose a lot of people and the trust and, well, the tolerance of a lot of people if we go with that. So it's ended up just being a touchscreen. And sometimes you have to take these very conservative decisions when it comes to that. And the same, I mean, it's the door opening worked very well because it was very obvious from the appearance of the robot to any bystander, oh, there's no chance this thing can open a door. So they perfectly understand that they have to do it. Had we put an arm on it and not used it to open the door, I can guarantee people would have very quickly said, like, oh, what's this rubbish? Why do I have to hold the door for this robot?
Okay, yeah. I mean, kind of going back to the engineering mantra of like under promise, over deliver, right?
Yeah, absolutely. Yeah. It's true. It's really important in this.
As well, you know, the old adage of trust arrives by foot and leaves by horse. You know, and it gets moved first impression once. We can all throw around those quotes. And yes, certainly it's always good to talk to your customers and your clients very early on, right at the start, understand what they want and, you know, what you can realistically give to them before you go off developing technology and developing their expectations too. One
comment, Oliver. One comment on this, Oliver. However, we had this first deployment of this robot in this care home, for instance, you know, where it was just this sort of information display and it ran around, and people saw that, and the therapists saw that. And it was not us to come up with the idea to use a robot as a guide in what they call the Nordic Walking Group. We didn't come up with the idea to use a robot in occupational therapy in that care home. They saw it, right? And because they were now immersed in an environment where they saw a robot doing something, they came up with an idea we would have never come up with. I think that's the other thing. We need to get these stuff, even if they are not, they don't solve every problem. But all of a sudden, they identify new use cases that become actually very useful.
Yeah, totally agree.
Absolutely.
I really like Lindsay the robot, and I do like it for personal bias. As I'm showing my screen now, that was the work of a PhD. This was the work of me as our master's project, and I can relate very much to the challenges that you describe. Most notably, if anyone has worked with the ROS or your 2D mobile robot stack, you'll put many months into getting it up and running, and then the first thing you'll learn is something called recovery behavior. And that's the reason why our robot is behaving very scared and just spinning around in circles for the most part, because you go through all that effort to make it work. And if the room's empty, it will freely, happily navigate from A to B, but with people around at a showcase there, it just can't handle anything really more than that little area that it's in. But yes, I very much appreciate and I admire the ambition of a tour guide, because it's a very good way of tackling some more of the, you know, lower level problems, I think, in this area, and like just get the solid A to B in human interaction before you then start thinking about other applications beyond the walking and talking. Yeah.
No, you're right. And I mean, we all have the same experience, I think, with the standard ROS navigation stack. It works fine for your nicely cuboid empty spaces. But that's what I mean. This is the human aware navigation part. And there's, you know, we've done some work on this, but others have done really, really cool stuff on crowd navigation, where they really model basically the flow of crowd. I don't know you're aware, but amazing stuff to also mathematically model how they basically flow, because you always must take into account that they will react, right? The crowd will disperse when you have a robot going towards them. And you want to model that, and you need this commitment by a robot to just kind of stick to its path. And this is particularly important the moment when you go into new museums. The standard navigation stack, which always says like, oh, everything an obstacle, I stay. I'm very careful. I'm not going to bother anything. You're never going to reach your destination. We've got school classes, 20 kids in there. You want to move carefully, slowly, but you want to move. Otherwise, you want to move to make them move, and then they will actually get out of the way. But you must do it very carefully.
Yeah, it's always if you're if you're navigating as a pedestrian in a city, especially in a foreign city, if you're crossing the street in Rome, it's not about being cautious, it's about being predictable. If you're trying to cross a street in Italy being cautious, you'll never get across. You have to be predictable, just walk and keep walking.
Yeah. That's why I'm very frustrated that I still haven't seen any autonomous driving trials properly done in Rome or in Athens or somewhere. They're all many of them are in the UK, they're in Milton Keynes, which I would consider a US layouted city. And I would say, I think the challenges are quite different. Or let's go to India, let's go to Dubai or somewhere. No, Dubai is probably easy. But yeah, whatever, there's certain places where it becomes much harder and where we actually hit the interesting problems.
Yeah, very much, train hard, fight easy, simulations, yes, are also there to make things more difficult, but you want to be training on rough cobbled streets first. And anyway, we've got another question from the audience, from Julius. Did you notice that people help more with failure recovery as asking frequency decreases?
Sorry, you dropped out for me for about 5 seconds, and I missed the hard part, the important part.
Did you notice that people help more with failure recovery if the asking frequency decreases, i.e. helped not helped ratio getting better over time?
I can't tell you, I can't give you a proper scientific answer on that. I can tell you the anecdotal problem that we had a lot of navigation failures in the reception area, in one part of the reception area. And that was unfortunately also the area where one guy worked, the receptionist, and they worked there for 8 hours a day. And this robot came past regularly, not always get stuck, would regularly get stuck, and he was fuming, right? He clearly said, "Oh yeah, I'm not helping this anymore, but it doesn't stop shouting, right? I don't care. If it gets stuck there again, I don't help it. But eventually I have to, because it just won't stop shouting and it annoys everyone." So we adjusted the volume level. And in particular, the most important thing we did is it doesn't shout into the void anymore. So we had human detection running anyway. So now we have the sort of, at least people need to be in the vicinity and need to pay some attention to the robot anyway. And otherwise you just give up and say like, well, I'm not, I'll wait until somebody shows up and helps me out here.
Yeah, I guess in the future the robot will have to recognize it's in this room. It might as well be useful in this room and try and help the receptionist rather than burden them in a further.
Yeah, but it's for safety. We can go all the way down level. All kind of inbuilt recovery strategies for move base had failed. It was still stuck. It still saw something. It may have been because it drove too close to a plant, and all of a sudden a leaf was in particular in that area. And then there is not really much. You need some human to assess the situation, whether it is safe to move or not, right? So you are somewhat stuck in some of these situations.
Okay, we do have one more question from the YouTube stream. You mentioned that you used Gaussian processes to learn recovery behaviors. Did you have to show the robot specific examples of how to get out of these situations and perform recovery? And he's asking where you can find out more about this.
Yes, so you can find more about this if you search "Don't Make the Same Mistake Again" and my name. I'm sure then you will be directed to the actual conference paper on that work. And so Gaussian processes, they are, again, a machine learning approach where you basically just learn, you demonstrate trajectories, and you can also demonstrate several trajectories, right? And you had to have a certain confidence before it would say, all right, I'm confident enough to navigate out of this mess myself. So it would probably, if you get stuck in this place, in this situation, it would actually classify the situation, for instance, a narrow gap. Right? If it says like, oh, this is a narrow gap, and that's probably why I'm getting stuck. If it has only seen one demonstration to navigate through a narrow gap, it wouldn't be confident enough to use it yet. But as the Gaussian, if you'd have to give several examples, they are clustered with this Gaussian process effectively as being from the same demonstration. And then you have enough confidence eventually to say like, right, I'm going to play back this mean trajectory based on the context of my sensor readings that I see. So it even works like if you've seen one typically encounter, let's say you go through a door that's very narrow, and then you approach another door that has the same signature, let's say in your laser scan, you can deploy the same recovery behavior.
Okay. Yeah.
Okay,
Well,
good.
Brings us, sorry, Michael. Yeah, I'll let you pass over to the next one. Marc, thank you very much. Really appreciate it. Wonderful presentation. Really interesting to see. Actually, for me, for my first time, a proper good look at what's been going on at Lincoln. And I had to come visit at some point.
Oh, you're very welcome. As I hope I also come down to yours eventually. It's been, I've been invited several times, and always the pandemic was in the way. Anyway, thanks to everybody, and enjoy the rest of the session.
Thank you very much.
Thank you. Take us away, Michael.
All right. After our keynote, next up we have Julius with Armstone, an autonomous mobile 3D printer. So Julius, go ahead, grab the driver's seat, and take us away.
All right, thank you. Can you hear me, and can you see the slides?
Yes, we can hear you and we can see the slides.
Fantastic. Great. So I'm Julius. I'll be talking about autonomous large-scale mobile 3D printing. So a little bit about me very quickly. I'm hopefully, fingers crossed, almost a PhD student, so I'm submitting very imminently. I have a maths and robotics CS background. And in this talk, because the robot that I'm talking about is a part of my PhD research, so I'll cover a little bit of the research background. I'll won't go into any maths in particular, but I'll just mention some cool things that maybe enthusiast robotics folk would like to explore or read upon. Hopefully I'll show some nice pictures and videos, and talk a bit about the design of this robot, and practice my public engagement, and so on. So the robot I'm going to be talking about is Armstone. It's designed and built as a research platform. It's a prototype type system, so it's not ready for anything in out there in the real world, thousands of miles away, remotely monitored or not. But it's designed to facilitate and make research easy for specifically for path and motion planning for relatively large scale autonomous mobile 3D printing. But before I can explain the design choices and what it's all about, I have to give a little bit of that research background. So this is going to be a slide that perhaps some of you have seen a million times, but this is very often how some research areas where they start. People look at in some industries like automation, automotive, and have noticed how incredibly well they've adapted automation, and how the factories of 50 years ago look entirely different than factories now, and so on. And then they look at their industry, and then they say, okay, so this doesn't happen here. And then they ask this question that there must be something missing. There's some missing information. What's the problem here? Let's create a whole research discipline that tries to address this. So robotics and construction, autonomous construction, digital fabrication, these research areas in one way or not try to tackle this kind of missing automation problem. And something that you probably have seen out there in the internet that gets people's eyes sometimes are these additive manufacturing solutions applied at large scale to building construction. So they're usually, these systems kind of originate almost as far back as the 90s. They're usually very large gantries or cranes, and they perform concrete 3D printing at incredibly large scales. However, if you look back at the research that started all of this way back in the 90s, that first described these machines, you actually find out that the vision that was laid out wasn't exactly the same. So I really like this quote that comes from 97, where it says that a large structure could conceivably be built by an army of mechanical ants, one grain of sand at a time. And there's several ideas here. So one is the parallelization of the process, but I'm going to set that aside, because before you can have a whole swarm of ants doing something, you have to have one doing something. So, but there's this other part of it where that the tool, or the ant in this case, the machine, is dynamic and smaller than the object that it's being built. Because if we reflect back real quickly, the lesson that we took from car manufacturing is this static tool, dynamic object one. And when we apply it to construction, that kind of just means that we just need to build bigger and bigger machines and treat buildings like objects, which isn't true. It doesn't work well. And if you flip this around and look at the kind of the scope of a landscape of research right now, you do see more systems emerging where the tool is the dynamic one, and it's moving in an environment much bigger than itself. And that's where mobile manipulators come up, and specifically mobile manipulators performing additive manufacturing and 3D printing, and hopefully utilizing the fact that they're mobile and they're in a very big space, and can deploy these kind of very agile robot arms performing complex tasks kind of throughout the workspace. However, at the start of my PhD, at least, when I looked at this, there were a lot of shortcomings to these systems, and the mobility aspect of these systems were very often underutilized. So with these early works, a lot of these mobile manipulators were just used to print. They were printing stationary, and they were just positioned in different places. Some of the later works started to do printing in motion, but they still had a kind of human prescribed tasks. But anyway, that was kind of the current state, and I might have or might not have read all of that. So I just kind of started building robots. I took a very naive approach as I just came out of a master's program and wanted to do something. So I just started building robots, and one of the first kind of robots that I built was just this simple setup of kind of a custom omnidirectional base with a KUKA Aiwa on it, and I tried to trace very long trajectories with it and see how much the end effector error deteriorates when you're moving the base versus when you're not moving the base. And the results were roughly positive, that there were comparable errors. However, was kind of experimenting with control setup in general. But the robot proved a bit too cumbersome, and then I had to build another one that was much smaller, based on, it was just a heavily modified KUKA U-bot. And in this case, I actually managed to get some deposition running on it. And in this the video that you see here is actually depositing some material that's much larger than it. So the big squares are 2 by 2 meters. So the overall, I think, arc was 4 meters long or something like that. And what I was experimenting there was modeling the whole system as a kind of giant redundant manipulator. So pretending that the mobile base is just a prismatic joint and a revolute joint, and letting kind of off-the-shelf methods take care of that. Well, and surprise, surprise, what happened is that it didn't. I was using a lot of the ROS ecosystem stuff, a lot of move it stack, and specifically with Cartesian, this palette planning with task space planning, what was available at the time was not making the cut. So I had to take a step back and do a little bit of work of myself. So I had to work a little bit on the pathliners, and I'm going to cover them in kind of a high level, and then hopefully move on to the robot itself. So if we think about what is it that we're trying to do, this whole mobile 3D printing, the fact is that we have a very long trajectory in space that we're trying to trace the end effector over. We have a mobile manipulator, and we actually don't care where the mobile base is, as long as the manipulator is able to reach the task and is able to print everything. We do care that, for example, as you print, you're actually creating the environment as you're executing a task, which is incredibly unique in robotics problems, because fairly often you assume some sort of static environment, or maybe model that constrains dynamically. But this is a kind of interesting relationship between kind of evolving obstacles that they're created as you're performing something. I thought is quite unique, quite a unique problem. So the first thing that I looked at is I tried to capture this relationship between the print task and the robot. So there are these very interesting works called robot reachability maps and inverse reachability maps. They're usually, they came from humanoid robots trying to position themselves to open cupboard doors and so on. So I applied that. So the reachability map is a way to assess within the robot local workspace, kind of like a little voxel, a little Cartesian point, and say how well can a robot reach that point. And if you have this type of data structure and then you convert that data structure, you can actually say, for a given point in the world coordinate frame, where should the mobile base be such that you can reach that point quite well. So these maps, these reachability maps and inverse reachability maps then can serve as a constraint for more commonplace path planning methods. So what I've done then is I've combined this with a custom rapidly exploring random tree approach with these sampling-based methods. And these were done in not only in spatial, not only in X, Y, and not only in base pose, but also in along the process, because something about 3D printing as well is that's a single directional process. You can't go back on it. So as you see this tree exploring, the print path in this example evolves from left to right, so from blue to green, and the tree explores along the print path, constantly checking and validating the base poses using reachability maps, and also sampling valid poses from the task, only given the task, using these maps as well. So at this point, if you have a nice planner that gives you a base path, and well, you have you know where the end effector should be, you can pretty much just assume that control is not a thing that you should be doing, and apply inverse kinematics, and voila, some sort of robot is supposedly doing something. Yeah, because simply by subtracting where you found the base should be from where the end effector should be, you're getting the local transform between the end effector and the mobile base. So you can just apply inverse kinematics. So at this point, it was all nice. But however, because of the two previous platforms lacked a bit of robustness, I had to yet again go back and build yet another robot. And I guess it's nice that I did, because we have something to talk about. Because I needed something a little bit more robust. So I'll give a little bit of an overview of Armstone hardware. So Armstone is kind of I don't know how to call it, like a human scale robot. It's about like I'll give the dimensions later, but it's about like a 1 meter, in scale. It's something that interesting that happened about it is that the design of the robot only took 2 weeks, and assembly of it took 12 hours. However, it really helps if you've been fantasizing about that robot for 2 years prior, thinking, how much better you could be doing if you had more freedom over the design of the robot. Then, of course, kind of the system integrations part, so getting all the software running, synchronizing your clocks, and all of the fun things that robotics people do. It took a while, and of course, the deposition system itself took quite a while as well. So something that's nice about Armstone, it has a very nice golden ratio proportioned mobile base, custom designed with aluminium extrusion. It has the X-arm, a manipulator that's placed on the robot, is placed at the bottom kind of part of it in order to maximize the reach at ground level, because the reach of manipulators very often deteriorates quite quickly as you go lower than the mounting plane. The whole chassis of the robot had like a nice custom aluminium 8mm thick aluminium mounting plate that was like laser cut to help with spread out the weight of the arm. Of course, there's a lot of momentum acting on the arm. There was a 20 amp hour 48 volt battery that's taken from an e-bike battery, I believe, which I think gave about roughly, it depended on what you're doing, but from 3 to 6 hours of runtime. There's several Intel NUCs to provide the processing power. There's some very old LiDARs. There's a nice network switch in there that I highly recommend called SwitchBlocks, helped perform the network switching between all the different devices and the control box of the X-arm and so on. Something that was very particularly difficult to design for me, because I'm not a mechanical engineer, were all the load-bearing parts. The whole robot loaded with material weighed about 40 kilos, which means there's actually, as it's moving at reasonable speeds, there's actually some serious load being put on the wheels. And I didn't do any custom machining or anything. So a lot of these parts, most of these custom parts were 3D printed, but I was fortunate enough that I had access to a Marc Forge 3D printer. So for example, this shaft coupler that was particularly difficult to design and get right, it was printed with nylon and I think reinforced with glass fiber or something along those lines. And then I used Maxon motors, which are kind of famous for being good, and VESC motor controllers, which should also be familiar to some of you if you do what it's called, longboard skating. I don't know, one of those skateboards with chunky hub motors on them and that you can control from a device. That's a very popular controller for those. The material deposition system. So I've the kind of goal of the design of the robot tried to assure that the scale we are working with is comparable to something that would happen in real construction. So I went with printing clay as opposed to just printing, making a smaller robot and printing plastic or something. So I have mobilized an existing system that comes from a WASP 3D printer that's designed for liquid deposition modeling with clay. So there's essentially a giant syringe system where an onboard compressor is creating pressure on one side of a cylinder, and that pressure is driving a divider and pushing material along a PTFE tube that then takes the material from the base of the robot to the end effector. And actually the PTFE is very important, and Reddit actually played a big part in helping me pick the material for that hose. And what else? Oh, and the material cylinder was still relatively small, about 3 liters, so not that much, and you'll see how big of a problem that is later. So the end effector itself, the extruder that I've used, was off the shelf. It's called Stoneflower 3D extruder, and the name of the robot actually comes from the X-arm manipulator and the Stoneflower 3D extruder, so therefore Armstone as a combination of those two. And there's nothing particularly fascinating about any of these placements other than this. The kind of software overview of the design. So the whole system used ROS in one way, shape, or form. And the thesis itself, the PhD work itself, specifically did not look at localization and mapping. So I've used I used an external motion tracking system. So there were markers on the robot that were able to localize the mobile base. So the robot was not aware of anything about its end effector, but only about the mobile base. The end effector was tracked independently to provide ground truth measurements. So having developed that path planner, that gave me a kind of global base path solution of where roughly the robot base should be. Then I combined it with some existing work where this kind of area of whole body control is being applied to mobile manipulators. So whole body control is very interesting. I highly recommend people to read up on it. Specifically, I've used an MPC style approach where there's an optimization problem being solved. So the future state of the robot, so what it's going to do over the next couple of seconds, is being predicted into the future. And then the very first control input is being used, and that kind of planning cycle is repeated at relatively high frequencies. So within this approach is quite good because it's optimal within that short time window. However, when you're doing 3D printing, you can often put yourself in infeasible situations, especially when you're deploying material on the ground and you can start to drive over it and so on. Therefore, that global sampling-based path planner that was developed before was used to inform that local optimal control-based approach. So they combined together. You have kind of like a rough guide where you should be, and then like a sliding window of optimal control of kind of how to roughly achieve what you should be doing. So I'll show you some results. Now, unfortunately, the videos are not working on the slides, so we'll show you like here. These videos are highly sped up, but so using this robot, I've managed to achieve relatively large-scale printing with clay. So this is a 2x1 meter scale of that bow tie shape, and I've printed 5 layers of the shape of in total 250 meters in length, the trajectory, the print path. The results being relatively good. I've achieved, I think, like 3 to 6, depending on how you're counting, and end effector positioning error millimeters. And I've experimented a little bit with different localization, but that's not particularly important. So the printing was happening at 4 centimeters per second. Yes, it was mentioned about 3 to 5 millimeter error with quite a bit of variance. Sometimes there were some instabilities or kind of aggressive motions. Something that's quite interesting, and to show that to you guys that maybe would be harder to show in more academic settings. So kind of close-up views of the issues with the system. So in this video, we can see there's a lot of vibration happening in the end effector, and that is where you get interesting GitHub issues with XARM developers, and that I don't think that is my problem right now. I think it's theirs mostly. Something else is interesting is the material refill. So you need to give a second for my buffer to go. Go. So because the material cylinder was only 3 liters, I had to manually refill the clay in the cylinder pretty much after every layer, which was quite a difficult process, as you can see. Like sometimes there was a little bit of leakage. You had to unconnect things, depressurize the system, like shove clay in, then after you're done with that, reconnect things, repressurize, make sure that the pressure is roughly, as expected. And even then you would then be introducing air bubbles into the system and so on. There's a lot of these finer details of things that don't show up sometimes in other works. However, something that's quite cool about the work presented is that both the path planner used and the control method used, they both support 6 degrees of freedom trajectories. So something that I was able to demonstrate is printing on normal to a surface. So trying to maintain the end effector orientation normal to a surface, and then doing non-planar printing. And there's still a lot of work to be done there, but it just demonstrates that functionality is already inherent in what's being developed right now. And in the interest of time, yes, I guess one of the final notes is that I have kind of the actual realistic application of this technology is still quite far off. There's many reasons in general why you should question additive manufacturing applied to construction, but even if you were, within what I've done, I've not looked at all into material properties, rheology, and so on. So you can see, for example, in this rotating image, where the end effector was and where the material ended up, there's a lot of compression, a lot of deformation, and all kinds of nuances that are happening. However, since I've built all of the systems, something that's very fun having had this kind of large project at the very end of your PhD is that it opened up so many interesting new things to explore. So something's really interesting would be to start looking at simultaneous additive manufacturing and mapping. So specifically, if you could maybe embed information and landmarks into the material as you're doing, especially as you're printing, especially with these infill curves, and also start using end effector mounted sensing to start printing not with respect to some global coordinate frame, but with local coordinate frame. There's of course this multi-agent system stuff that I've explored a little bit. I'm just finishing up, and there's stuff that you can do to upscale the whole system. But however, because the PhD is over and there's no more money, and because I also had to finance this whole thing myself, I'm most likely going to end up selling this robot by parts, because no one's going to buy a mobile 3D printing robot. And that's it. Thank you. I don't know if there's any questions.
Right, well, I just want to say right now, if I had the disposable income to buy said robot, I would. Yeah, I know the pain of having to disassemble it for the next robot or those things. We do have a few questions. Yeah, fantastic presentation. Really interesting to see kind of where this kind of work is at the moment, because it's going to be realized one day. And we do see examples of 3D printing of houses, and they're often very much glamorized. And you see the news interview, and you never see the journalist go back 6 months later and inspect the walls for damp. Yes, Michael, do you have any questions, or should we go straight to the comments? We can't hear you, Mike. Okay, in that time, whilst he checks that, I will ask a question from the audience. Why would the problems in the system not be interesting in an academic setting? I'm only an undergrad right now, but wouldn't the problems also be relevant?
Problems in the system, meaning with design challenges.
Not be interesting in it. I guess this person is trying to just kind of understand why there's not a greater value in an academic setting for this. Why, if you're talking about, the out of funding for this.
So essentially, it's a challenge in academia itself. Perhaps I'm not the most right person to talk about this, as I'm just a PhD student.
I can help with the answer if you want to, but I was going to let you myself.
Yeah, I mean, I think I'm going to say for any academics, it's going to be a very common answer. There's a huge bias towards positive results in publication. There's an issue. A lot of these problems, it's really hard to trace down what exactly is causing it. And it would end up being an uninteresting result to an extent. There's like a little vibration, and then you're going to do an enormous multivariable analysis on it and find that you had a screw loose, like on your third joint or something. It's not so. There are system development issues, and especially then there's an issue presenting what's called the systems paper in the robotics community, especially, where are the type of papers that don't particularly improve a given area of mathematics or research or so on, but present a pipeline that's of something being achieved. And those are sometimes, and those are kind of harder development problems, and they are a coin flip in my personal experience. And I don't know what you think, but there are coin flips. Some people like them because they think they can be valuable. Some people will say you have not actually done anything.
Sure. You highlighted, you've touched very quickly then on a lot of different issues of academia. From having friends of mine in industry and academia, there are pros and cons to everywhere you go and work and whatever you do in life, it seems to be. And a lot of those problems, you'd like to think, are unique to where you work, and they're not. They're everywhere. I think to answer the question a bit more directly, towards the end of a PhD, if your work is doing well, it may be a case where you can apply for larger research grants or more funding, but often the way of a PhD is just that student will then go on to a postgraduate position somewhere else, or then into industry somewhere else. But anyway, this is getting a little bit off topic. Another question. I've always had vibration problems when using Meccano wheels. Yep. How did you go about solving this?
I didn't. They are present. However, they are so I've actually as an experiment ended up trying to 3D print using TPU, which is a flexible material, the mecanum rollers to introduce compliance into the wheels. That went horribly. Don't advise it. What happens with TPU, it deforms. So after the robot was left stationary overnight, the next day actually there were flat parts on the rollers. However, absolutely, vibration is a problem in the wheels. The vibration I'm witnessing is still there when stationary, so I've checked that that's not the problem. And it just, I have instead a very slightly dampening part where the motor mount meets the chassis, the aluminum extrusion chassis. So there's a tiny bit of compliance over there. I don't know, to be honest, how much that is helping, but I'm not seeing a lot of in this particular system. I'm not seeing like highly significant, or that is not the dominating factor that's causing my error, I believe. In my previous, in the UWASP one, that was a very big source of error. That robot was a big metal steel part, so it was just like propagating straight in. Sorry, maybe not a full answer, but yes, Mecanum is
no, that's very interesting. And I imagine that as you highlighted again, it would be great if this work was continued. Often, good robotics projects, everyone wants to see their project live rather than die. But you could see how if a future PhD student were to take this on, they could work on swerve drive and replacing the Mecanum wheels with a more efficient, a better method for that task, and those kinds of iterations. Michael, do you have any questions? You had the mic back then. What went wrong now?
How about now? Can you hear me? Okay, wonderful. So sorry about that. My computer crashed. I had to come back. Yeah, I had a question about why you landed on clay 3D printing as your kind of test case here. I as much as I love the idea of clay printing, I think the current state of the art is a lot less reliable and a lot more difficult to use than polymer 3D printing. So I was curious kind of what led you down that road.
So mainly it was because I wanted to have a placeholder that is within reasonable scale and kind of affordability to kind of simulate concrete. Now, so if I guess at the time at least, I could have done a smaller robot with FDM type of printing with PLA. I know there are bigger extruders that can do, I don't know, 5 mil, 6 mil printing of plastic as well with thermoplastics. I was a bit scared of them because they include heated elements at the extruder. I thought that would require a much more complicated design that I would have to either do, and it's hard to get off the shelf. So it was essentially like the most simple answer. It's less of a design choice. It's more of a circumstance choice. Like what your university has, what you can afford. You cannot do clay, but you can maybe afford to buy. Sorry, you cannot do concrete. You can maybe afford to buy some clay. An auger screw in a cylinder is a cheaper extruder and simpler to work with than thermoplastics and heated components and so on. So
Absolutely.
it's mainly about that.
Okay, that makes sense. And that is all the time we have. So thank you so much for your presentation.
Well, do we have our next presentation? The next one, camera-controlled hexapod, is that person here? I don't think they are.
I don't think they are. You're right.
So we can go a little bit longer, and then we can hand over to Keegan, because I think we can get a couple more questions. I've certainly got a couple. Is that okay with you? Yeah.
That's great with me.
Cool. So I mean, personally, I wouldn't agree with what you said about plastics being more difficult to work with. Certainly, that any off-the-shelf 3D printer like the Ender 3 that I'm looking at has a Bowden extruder. So there's one motor that's extruding it, and then the reel of plastic. So I could certainly see how you would fit that onto an standard arm. But at the same time, there is a more nascent earlier on industry for being able to print in concrete, yes, for construction, but then ceramics. And if we can start printing ceramics, that opens up a lot of new doors for manufacturing applications that we currently don't have. Brake pads would be obviously a very interesting one. If you could 3D print those, you could get much better cooling out of it from an airflow design, things like that. Michael, do you have another question, or should I bounce one?
Yeah, I have one more question I could ask. So, on the subject of introducing kind of vibration into the system through the mechanism wheels, did you experiment at all with any kind of like print, then move, then print kind of a mentality? Instead of trying to maintain printing while you're trying to move the base, have the base be mobile overall, but then be stationary while the arm is actually printing?
I very deliberately did not. that was like a design purpose, because this work is like, I was quite captured by the idea of printing in motion, and that's exactly what I wanted to do. However, there's really good work coming up at TUM, so Technical University of Munich. They have a very big project there. And they do. They've recently published some stuff using, I think, a Robotnik base and a UR12, doing printing with stationary stuff, and also so you move print, and also a university in Singapore. So one of the pictures that I showed had some of their earlier work as well. Did that. I think it's really, it will increase the robustness undoubtedly. But I'm just really interested in how do you get this continuous process happening from motion and path planning perspective. With mobile manipulator doing for something much larger than yourself. I think that's just a really interesting problem.
Couple more questions. One which I think has already been kind of answered earlier. Are there plans to proceed the project, such as going to a startup? But I think you've already kind of discussed that you're not in a position to take this further at the moment. The other one is, how much of the design would need to change to accommodate concrete or ceramics? So if you wanted to take that, robot as it were, and then move up to concrete, would you need to replace the arm, or would you just be, how would that go?
In a research setting, the deposition system itself would have to change. The arm payload is maybe close enough. So XARM 6 has, I believe, a payload of 5 kilos. Obviously, as all arms go, that's unlikely to be at all speeds in the whole workspace. So maybe if you're able to have an extruder that's quite light enough, if the weight of the material in the hose itself is hopefully distributed along the manipulator, the X-arm itself might be able to do the trick, but that's a bit of a risk. You would have to add, most likely, a tether to start feeding the material off base, because it's unlikely that it would be able to take a reasonable amount of concrete on there. Ideally, you would start scaling up the system. So the best example of the type of scale and kind of system you would be looking for would be, there's a project called an in situ fabricator from ETH Zurich. Has a whole bunch of papers on it. If you look that up, it would have done bricklaying, welding, all kinds of things. But that's the scale of the robot that you would need to start doing something like this.
You'll get to see some in-situation welding tomorrow for our keynote speaker for the bio-inspired robots category as well. That's one to look forward to. Okay. I think now is a good time then for us to hand over to our next presentation. Michael, is that cool? Right, wonderful.
Absolutely.
So next up we have Keegan Neve, who's going to be, I hope I pronounced that right, if not, please correct me, who's going to be presenting the robot NE5.
Yes, hopefully I'm coming. Yeah, the window's just highlighted saying it's picking me up, so that's fine. So, thanks for inviting me along to this. I think one thing that's been heartening so far is hearing a few of the other presenters say the titles of their videos of how not to do this and how not to do that. Lessons learned are incredibly important, and I've done a couple of how not to do videos on this robot as well, so it's very much in good company. Now, one thing I will say is I don't have any slides. I got incredibly cocky and was expecting to do it all live demo. I've got multiple cameras rigged up, my little arena on the floor, and my robot's just not playing ball. So I'm just going to wing it, basically. So my name's Keegan Neve. I run a robotics company called Neve Engineering. It's me, basically. I'll be completely honest with that. I've been running for a couple of years now. It started off very much as a hobby and then kind of got a little bit out of hand, as I'm sure plenty of you can actually relate to. A bit about my background. I saw short circuits when I was a child, and I never quite got that out of my system, as will become obvious, and the name of the robot as well. I've got a background in I started off as a developer support engineer at Microsoft. So anybody who called in with problems with Visual Studio, I was actually one of the support engineers for that, which was a trial by fire, I'll tell you that. Then I've been working as a software engineer and data visualization engineer for it was 7 years at the Satellite Applications Catapult in the UK. I used the Unity games engine to develop things that really shouldn't have been done in the Unity games engine, but they work a treat, like taking data from from a constellation of 11 satellites to track the position of every boat around the world and visualize that to try and figure out which of them were fishing illegally. It's a bit mind-boggling saying it now and looking back, but it's a thing we did and it worked. Unity still aren't sure how we did it either, but over the course of while I was working there, my interests kind of came back to robotics. They kind of got a bit burnt out of me at university for various reasons. But PyWaz came along, which is a robotics competition primarily initially ran in person in the UK in Cambridge. And I applied for the first time. Every time before that, I'd heard about this competition afterwards, and it was absolutely fantastic. Next year, I'll apply to that. And then I either hear about it just after it's finished or just after the applications have closed. But this time around, I got in. This was at the end of 2019, and I was really excited. And I built my first robots, the predecessor to this one, and got everything almost working in the run up to March 2020. And the first lockdown in the UK happened a week before the event was due to happen. So unfortunately, that was postponed. It then went online, and they've done it virtually for the past couple of years. And this is kind of where I've got to with the iteration of my robots. I also have a considerably bigger robot I'm working on. This is the plywood monstrosity in the middle is a cargo robot I'm working on called Anywhere. You'll see the pattern with my naming. I do like my puns. Like this is my custom controller, and it's called Anything because that's what it can control. I apologize for nothing. But yeah, so this is NE5. This is kind of my pride and joy and where it's got to so far, even though it's not working today. And I'll take him out back and give him a bit of a kicking later and figure out what's going on. But this is, it runs on 2 Raspberry Pis. So we have one up in his skull. And this is still one of the greatest innovations I've made on this robot. It's magnetic and it just kind of clunks on the top. So if you've not heard of this, it's a stereo Pi board. It runs on a Compute Module 4. And I'm not going to tell anyone where I live because frankly, they're like gold dust at the minute and I'll probably be a part of a heist in short order. But it's with the compute modules, it's able to break out the 2 camera ports. So you can actually do stereo vision using this. Now I've got basic disparity maps running, but not actually generating depth maps yet. So yeah, the rest of the hardware is we've got the compute module 4 up there, and in his caboose, in the back here, we actually have a Raspberry Pi 0 to W. They're connected using a USB cable in gadget mode. So this is actually gives us, I think it's something like 0.3 milliseconds ping between them. So it's very quick to get messages between the caboose and the head. And basically the idea is that the Raspberry Pi in the head, I think it's got 4 gig of RAM. It's going to be the kind of the higher level control, like map generation and path planning and things like that. And the one in the back actually has a Red Robotics Red Board Plus on the top, which has 2 motor controllers plus an extension board for another 2 motor controllers, because we've got 4-wheel drive on this one with mechanism wheels. And yes, I'll echo the words of the previous speaker. They can be a nightmare. Very useful though when they're slewing all over the place. It's a lot of fun as well. So yeah, the Pi in the base is kind of doing the legwork, literally, I guess, with the wheels, and also connects to a servo expander board up behind this chest cavity here, which controls the arms. So on here we've got two 6-degree of freedom arms. They are at the minute, because I try to get as close to both human and Johnny 5 as possible, just because I'm a sucker for punishment, I think, more than anything. This is all using off-the-shelf hobby-grade servos at the minute. The initial plan was to tap into the potentiometer on board these. If you open up the servo, you can actually literally just wire an extra wire to the potentiometer, hook that into an Arduino, and you can get position data back from the servo. I then discovered the tiny Dynamixel servos that have got all of the control built in for 20 quid a piece. And for the amount of time it's going to take for me to actually get these working, and then have to remake them when I inevitably mess up and have to burn one out and so on and so forth, which I've done here more times than I would care to admit. I just figured I'll kind of upgrade to the kind of the more professional level of kit, and also has a linear actuator. So same with Johnny 5. It can actually kind of stand up to, I think, somewhere in the region of 8 feet at full height, but crouch down, and the laser turret comes over his shoulders. His eyes go red, and funnily enough, these are NeoPixel rings. And yeah, so one of the challenges for next year's Pi Wars, which is what we were supposed to do in 2020, is basically a Nerf shooting gallery. So that was totally the plan for it, was having the shoulder-mounted Nerf cannon that came over. I've got to the point where I want the robot to work, but if it just looks really cool while it's doing something at the event, that's kind of enough for me. The number of people who've kind of been inspired to kind of, for one thing, join Pi Wars, a number of my friends have signed up after seeing the incredibly daft thing I built. If I can kind of help inspire someone else, then I'll just call that a win, because that way, if I've not managed to get anything working, that's kind of just a cheat. I can just say, oh no, yes, but clearly we're all winners here because we've got someone else involved. So that's kind of the overview of the robot itself. For the software that's running on it, it's Raspberry and running on both Raspberry Pis in there with ROS on top of it. And yeah, funnily enough, I'll be a surprise to no one, considering I'm on brand with my t-shirt. So currently it's running ROS Noetic, just because that's what I built the previous version for, and it's just kind of developed on top of that. For next year, I'm going to start again and switch to ROS 2, because it's just so much more developed now than it was when I first started working on this. And yeah, so that's kind of an overview of the thing. I've got a couple of videos of it, actually, how it was running in the competition. So if I do this and mute it, there we go, and share my screen. Hopefully this will just work. And there we go. So this, what you should be hopefully seeing now is my submission for one of the challenges, which is called Nature's Bounty. So the idea is that all of Pi Wars was themed around agriculture and agri-tech this year. So we had Nature's Bounty, where you had an apple tree in the middle of the arena. You had to go along and collect them in whatever way you could, basically. And for this one, I thought that I'd be on for a winner, because I'd be able to use both of the arms, grab them at the same time. And it turns out that because of the size of the tree, if I tried to use both arms at once, it just couldn't fit in the space. So what I instead ended up doing was having, you can see the mechanism wheels coming into play there as well. I had basically this keyboard with, along the top, so that was the top. So for the top line of the keyboard, I had QWER, which was, move the arm up to the top, then close it, pull it back, and then the final one, as you can see, the robot holding over the basket and dropping it in, and then moving on to the next one. So it wasn't what I was hoping for with full autonomy with using the computer vision to grab it and all the rest of it, but I got a lot closer than I had in previous years. A few of the lessons learned, I guess, I think these are the ones I always like to share, because if nothing else, if I end up watching back of my own videos, I might finally learn the lesson I'm trying to share to everyone else. The biggest one I've learned this year is if you're using servos on something 3D printed, which this all is, what if you don't 3D print servo horns? And seriously, future Keegan, if you're watching this, just don't do it. It never ends well. So a couple of these horns are actually super glued onto the servo, because at 2 o'clock in the morning, when I needed to get the videos done, that was just the only option. What I should have done is actually put receptacles on the back of the 3D printed part, so you can attach the part to the horn that came with the servo, and it's just a lot stronger that way. The other thing is Wi-Fi is a nightmare. So with this controller, it was connecting to my Wi-Fi access point, same with the rest of it. And anytime I go anywhere else, to an event or to a friend's house or anything like that, trying to connect everything to their network, it was just a no-go, basically. So one thing I've actually done is I've got a second USB wireless adapter in his head. He's actually acting as a wireless access point. Everything connects through to him. I can then connect the other Wi-Fi NIC through to my friend's Wi-Fi or the event Wi-Fi. Everything, including my laptop, has access to the internet, and it's just so far seems to work really well. How that'll work at a big event with lots of other people there, with lots of other Wi-Fi stations, and who knows what else. Who knows, but we'll figure that out and have a plan B in place for that at the same time. And yeah, the other thing was the controller. I think I had a problem with this. Internally, we've got a Raspberry Pi 4. It's broken out at the back with all of the connectors. We've got a USB-C charging point in the back as well. It's got a 12 amp hour battery in here, just because it was a few quid more, and it's a considerably bigger battery, and it'll do the trick. The controller part, the joysticks, both of these and all of the switches are connected to a TC 4.0. And I had a problem with that, where after a few minutes or 10 minutes, it was variable, which was really annoying. It wouldn't, the computer, as far as the Raspberry Pi was concerned, the joysticks were still connected, but they weren't getting any data. So you can move them around. The serial port would show that things were changing, but over the USB port, which was acting as a human interface device, nothing. After a lot of digging through the forums, it turns out you've got to go into the teensy USB definitions and change the joystick interval from 1 to 2. And then it just works. And by that point, I couldn't be bothered to try and figure out what was going on. I just accepted it and moved on. So as a backup, I was actually using USB Xbox gamepad plugged in. And that worked a treat. It was just annoying that I couldn't use this beautiful controller I've made. But that's kind of part of the original plan, was that having the USB on the back and having the ability to plug in a second controller, it means that somebody could be controlling the arms, moving the head around with this, which is also free access on both these. So you can actually move the arms in 3D space quite intuitively. And somebody else could be driving with this. So you've kind of got the buddy system built in by default. Yeah, but that's kind of the next steps on this are to kind of rebuild the arms, and with the Dynamixel servos, which also have the benefit of not having all of the wires in the world coming through, because you can daisy chain them, which will help a great deal. Just generally tidying things up, finally getting the cameras working, so we want this to go fully autonomous. Not only for Pi Wars, but for as a telepresence robot, being able to control this using VR, which I've done again at my previous job. With all of the depth map generating the environment in 3D, I've already kind of got that sketched out. I think that'd be a really powerful and relatively cheap tool for further research as well. So as much as this bit has been a lot of fun for Pi Wars, it's acting as a portfolio piece for my company going forward as well. When I'm finally at the point where I'm not embarrassed by the state of the 3D files and some of the code attached to them, this will all be released open source. On my GitHub, which is github.com/neaveng, Neaveng, there's a simulated version of the robot already available with the URDF, with some of the basic, the core codes to actually get it running around. And I've actually been able to get it running around in Gazebo, generating the 3D maps, but just not translated that over to the actual working robot yet. Working robots. But yeah, I think that's kind of a big overview of the robot, of me, and I've completely lost track of time. I think I'm at 15 minutes, so hopefully 15 or 20 maybe.
Well, I will say, yeah, a couple of things for, I think for the audience. One, as I didn't prepare a presentation, I'll just wing it goes. That was very impressive. That was a very, very good off-the-cuff presentation.
I've got the gift of the gab, I've been told.
The counterpoint, that is, of course, folks at home, doesn't matter how good you are or think you are, it doesn't hurt you to not have a presentation or some videos to hand. I really like the robot. Yeah, it's a good, fun little thing. One thing that immediately comes to mind for me is a presentation we had last year by a couple of people for a robot, which I think met into a similar kind of, not demographic of robots, if you will, for a small kind of size open source project. Theirs is going a different sort of direction, but there's a lot of things there. I think there's a lot of kind of good compare and contrast there as well. One big thing as well is you're very much using single board computers throughout, and I didn't hear any mention of any microcontrollers. So anything you'd like to say regarding that?
Yes, I basically ran out of time. So there's a teensy in here, which is, like I say, acting with the joysticks. There is embedded in there somewhere a currently unused teensy as well. So for the position feedback from the potentiometers in the servo, the idea was to got a permaproto board on his back there, which has the connections for the various servos. And the idea was to have basically in the space over here, so I think that's a left arm and that's a right arm. In the space left there would be a big plug that would hook through to the headers on the teensy to actually use the 18 analog to digital converters on the teensy to get those positions through. It was also going to do encode the wheel encoders, because they're not currently hooked up either. So yeah, it will have one at some point. And again, because you've got in the same way I've got the 2 Pis on there already, having something that is quite cheap, relatively speaking, like the Pi Pico alone is, like 5 or 6 quid or something daft like that. And even if you went for the teensy, you've got a 600 megahertz processor for 20 quid, which is, I mean, I grew up and my first computers I worked on were BBC Micros. So I kind of was right at just riding the wave as everything kind of developed to where we are now. And thinking back to what we had then and what we're now able to almost, sadly, a lot, people see them as just disposable to a certain degree. But the fact that you can just order a strip of, Pi Picos or teensies or things like that for relatively cheaper for the power they've got is just mind blowing. But yeah, so there is a place for those, and that's in a place where I have more time to get things working. So, yeah, it's
just very, very often there's for the robots, especially in these kind of sizes, that and I'm not the only person in the world. There's obviously but Michael will chip in as well his thoughts on it too. Having a single board computer to handle your higher level computation, your sensors and that kind of processing, and then microcontroller, do the lower level, motor control, the bare bones stuff. maths that has to just run again and again, low power consumption. That's where you can get that kind of nice, trade-off between the two. But Michael, what are your thoughts as well?
Yeah, well, so I was just going to briefly relay some of the questions that we had from the YouTube chat. Someone was asking, how do, not just you, but I think a lot of people on the presentation, I guess, docket today, how do you find time to have these kind of really cool, intricate hobby robots and balance that out with your day job and balance the burnout that comes with both those things?
Burnout, very good question. Badly. So, I mean, I'm incredibly lucky the position I'm in. That when I was working at the Satellite Applications Catapult, they actually let me go part-time to try and get the robotics side of things up and running. I think I'm probably one of the only people from PyWars who joined the competition and then a year later quit their job as a result of it. But I've got to the point where I'm able to take on a couple of contracts to kind of pay the bills, keep the lights on, and try to do these with the rest of the time. That's the intent anyway. But with as many of the hobbies I've got on, like the big robot over there, that if anybody's read the Discworld novels and they're aware of the luggage, just stay tuned because I'm working on that. I've actually got a set of legs that bolt onto the wheels and working on a model chest to go on the top of it. So I'm not able to concentrate on one thing at once. And funnily enough, 6 months ago, diagnosed with ADHD. Who'd have thought it? So I think I just try and get done what I can. When PyWars comes around and the inevitable deadline, there's that burnout that comes when you realize you should have done a lot of things already. But yeah, it's
always, it's something that everyone experiences in this industry and many others within science and technology. And outside of that, you get into imposter syndrome. It's, how far do you want to go into the conditions of our society? And, but I think one thing that I've certainly appreciated is that it's maybe very tempting, especially when you're younger, to push yourself very hard, to work as hard as possible and get those results. But if you want to be in it for the long haul for your career, you will need to not just accept that there needs to be a balance, but learn that you need to prioritize your physical and your mental health and seeing friends and those kinds of things too. And that doing those kinds of things as a priority will then actually turn out make you better at the robotics.
100%. I mean, there's this running horrible self-help type thing of find a job you'll love and you'll never work a day in your life. And that is, there may be children present, so I'm not going to use the words I'd like to.
You'll learn to hate the job you love.
Well, it's the other problem is if you love what you do, you won't realize how hard you're working, and you will just slam yourself straight into the wall. Like the illegal fishing project I mentioned. If you do a search for Project Eyes on the Seas, you'll see the scale of that was involved, and we were doing good work. We're all hackers. We're all just kind of given this really random problem to fix. And I was certainly working all hours trying to get it working for various events. And it didn't do me any good. And it didn't do any of the others any good either. And we all learned the hard way that you do have to look after yourselves. And it is, there's, especially in like the games industry, you've got the crunch, which is somehow an expected scenario, which is just horrific. You've got to look after yourselves. You really do, because
that's some very good advice. Thank you.
Very hard earned.
Yeah, we all learn it some way or another, I suppose.
Yeah.
One kind of more specific question for the Wi-Fi problem that you were discussing earlier. Is the guide to the solution you found, is that available? Would you mind sharing that? One of the
I've written it up, and if you go to neve.engineering, that's the URL for my blog. I've got a problem with the blog where it's read only at the minute, so I can't actually write any posts up. So I've got it ready to go, and as soon as I've fixed the blog, I can post that as well. So if you follow me on Twitter, that's where everything kind of gets. That's kind of my central location, and that's Neve Eng. Yeah, like I said, had I slides, it would have been a lot easier to see as well. But
yeah. Well, yeah, thank you. And then I guess one question from me, as someone who's like kind of neck deep in ROS, it seems like you're using their tools as kind of the foundation for the platform you're building here. What are your thoughts on some of the more recent transition efforts, ROS to ROS2 and Gazebo to Ignition, stuff like that? What are your thoughts on that?
I've been trying to follow it just for when I do take the dive. Hopefully it'll be a bit easier, but I think a lot of the problems that I've had with ROS1, with networking, as I end up, them will go away just because it's a lot more peer-to-peer, so you don't have to worry about everything knowing exactly where everything else is. And yeah, I've learned a lot of problems that way. But it seems that where ROS1 was initially built by is it Willow Robotics, way back when for a specific problem, they built on top of that, and then they kind of had the legacy issue where everything was built on top of good intentions, and it works a treat, but the developers themselves have admitted that they need to kind of draw a line under it, start again with ROS2, and that's what they've done. So I'm hoping that a lot of the problems will have gone away. No doubt there'll be new problems because I think life can be too easy otherwise, but yeah, it seems like they've made some promising steps for sure.
Great. Yeah. No, I'm glad to talk to someone who's hopeful about it. I've heard mixed reviews.
I'm nothing if not an eternal optimist, I think.
Yeah, nothing's ever, all good or all bad, but it's great to see that they're really making the effort to, like, as you said, make things more peer-to-peer and more stable. So it's really good in that sense. We got a few more questions from the comments. There it is. Could you talk a little bit more about the big robot in the corner of your garage that you mentioned?
Yes, yeah. So this started as a joke. So there's a big nerd convention, which is basically my spiritual home, which is called Electromagnetic Field. And basically in 2016, we were camped just far enough away from our cars that it was just annoying. And we joked about how great it'd be to have a robot that could just follow us around and to carry all our kit for us. So I came up with the idea for the luggage from the Terry Pratchett novels, wonderful human that he was. And it kind of grew from there. And since coming up with the idea for that, I also started something called Hacky Racers, me and a few friends. If you're aware of the Power Wheels racing series in the US, where they take the kids ride on toys and soup them up and race them against each other, we're essentially doing that in the UK as well. So yeah, Hacky_Racers on Twitter, and give us a search on Facebook, you'll find us. We're also trying to start an autonomous league, but again, that's a different topic for a different thing.
Very cool.
But this was going to be my Hacky Racer with the wheels and everything. I ended up becoming the compare, and I just love it too much, and I let everyone else race and just take the mick out of them while they're racing, and that just seems to be my niche now. But the carrying around of all of the junk is still quite tedious. So this is kind of the result of that. It's got 6 off-road hoverboard wheels on it, 3 O drives connected by a CAN bus, and up top it has the beacon there. You can see is it's got LED neopixel matrix in there, so it acts as a kind of a warning light, and also a U-Blocks multi-channel GNSS receiver up top. So that's coupled with a base station I have on the roof here at the minute. I've also got a portable version of it, and a little remote control that actually sits on my belt with another antenna on my shoulder. Combining the 3 together with the correction data from the base station, I could get down to 10mm accuracy. And basically, if I press and hold a button, one second. Hopefully you can still hear me.
Yeah, we can hear you fine. You sound fine. Yeah.
Yeah, my Bluetooth headset died. Yeah, so the idea is that press and hold the button, the robot will be able to to kind of just follow me around.
and also have a manual joystick on the top because I'm using a nunchuck for that. So I know it can carry my weight because I was using it as a step ladder at one of our events recently. So the plan is for it to be able to carry around 100 kilograms because I want to be able to ride it. And that's about how much I weigh. But yeah, that's kind of lots of moving parts with the GNSS, with all the different sensors I'm going to put on it to try and, well, make sure it doesn't hit anybody. That's a different scale of problem, but I'm really looking forward to doing it. And if nothing else, just saving my back from not having to carry the PA system and the other thing I've just got, which is terrifying, which is 6 LG Chem batteries from a Jaguar I-Pace. I'm building a big battery bank for hacky racers so that we can charge all of our vehicles without having to plug in. So yeah, if anyone's got a source of cheap solar cells, I'll gladly take those off your hands as well. So yeah,
that's some cool stuff.
So many different tangents. I don't know where to begin or end with half of these. So hopefully that kind of covered some.
You're good. This is we love. I mean, the best presentations are the ones that are filmed in someone's garage, right? It's just great to see the thought process laid out.
Well, this would be another one in its own right because I'm actually sat in 3 different cargo containers that I've welded together and use the plasma cutter between. It's
even better.
I don't make anything easy for myself. I really don't, but seem to have a lot of fun getting there.
Well, so one more question. If you could relearn, ROS 1 or ROS 2 from the beginning, how would you go about it? What were some of the tools that you used that you found the most helpful?
Are those tools still in date? I mean, if you're relearning from the beginning, if everything moves so quickly.
Yeah.
Yeah, true.
I try to learn from tutorials on YouTube and from the tutorials on the website. And I think, reading through the various forums, and ROS isn't trivial. I think that's kind of one of its biggest hurdles is the learning curve is quite shallow. Most people say it's quite steep, but no, this is shallow. It takes a long time to kind of get the basics working, or at least it did for me. And then it kind of speeds up a bit. The biggest thing I did was signed up for the Construct for Robot Ignite Academy. Not sponsored or affiliated or anything like that in any way, shape or form. It's just they've got it's about €35 a month or something like that, but they've got IDEs all built in, in a web interface with the graphical user interface that you remote into and the tutorials and everything else. And they're constantly updating those. They've got a bunch of ROS 2 ones available on there now as well. I think I would have basically gone there a lot sooner, just because that was the biggest help. I learned by actually having, by getting my hands on. If I'm just trying to read from a book, I'll never learn anything. So I think that worked for me really well because you've got all of the code examples there. The forum you can ask questions in as well. So that's probably the other way. Other than that, if you can find a cheap ROS robot that already works, rather than having never used ROS in your life and then trying to develop one completely from scratch, that's probably a good idea. So get like something like the TurtleBot 3 or 4 or whatever the latest one is out. Get something that is known good and known working, because otherwise you don't know where the problems are. They're probably the 2 or 3 or however many lessons I've learned from that.
Yeah. Well, great. Yeah, some wonderful advice. More wonderful advice.
We definitely back that. Yeah, it's obviously you do have to do your homework in advance for online courses because there's a lot out there, and anyone will take your money if you're willing to give it to them. But there are some fairly well accepted courses now that are just fantastic to look at, and they will cost you. Often now they're free. And they're only cost money if you want to actually have a human on the other side giving you feedback and a certificate at the end to pay money for it. So online courses for these kind of things, if you do your homework and make sure to check the reviews, can be really good for not just ROS, but most of the skills.
Most things. Yeah.
Second to being able to go to university or a job where you can work alongside other people and professionals who can teach you one-to-one. That would be the Okay, so our next presentation is also a no-show. That's okay. We had anticipated it. So, Kamal, are you ready to present? Are you willing to start a bit earlier? And I think that's probably for the best because we had you slated for a mini presentation, but I think considering what I saw earlier on the preview, I think it'll probably be good to give you a bit of extra time.
Absolutely,
I think you've probably got a bit more than 10 minutes worth to chat with you about, so be excited what you've got.
Yeah, that should be fine. I prepared it for 10 minutes, but maybe I can talk a little longer. So we'll see how that goes.
Sounds good. Thank you again, Keegan. Wonderful presentation. And
yes, thank you very much.
Oh, no worries. Thanks for having me.
Wonderful. And Kamal, when you're ready, share your screen and take it away.
Yeah.
Yes. 1 second. Okay. Can you see my screen fine?
Yep, you're all good.
Yep, we got you.
All right, so I guess I can take it away. Since I got a little more time, I could be a little bit more in depth here. So hello, everybody. My name is Kamal Carter, and I'm happy to have the opportunity to present my aim hack robot for the Reddit Robotics Showcase. Yeah, so I'm 25-year-old. I work at a robotics company. In my free time, I try to build cool robots for YouTube and just to learn more about robotics in general, even after going to college for it. So still always so much more to learn. So yeah, today I'm presenting my aim hack robot, and it's a physical aimbot that's going to work in aim labs. So I'm an avid video game player. And I've been playing shooting games for a long time. I remember playing Call of Duty Modern Warfare 2 back in like 2008. So that's one of my favorite genres of games, and shooting games kind of like really popular right now. So you got really big games like Fortnite, Counter-Strike, Valorant, Warzone, and Apex being in top 10 most popular games out right now. So the one big thing about all these games, they take very precise precision to be good at, and a lot of time to practice. So people put a lot of time and practice into them getting really good at the game. But that's a big problem for me because I'm really bad at these games. I'm really bad at aiming in games. My friends always make jokes at it. So here's my KD ratio in Call of Duty Warzone. It's a 0.61 kill death ratio. So that means for every time I die, I'm killing somebody 0.61 times in games. So that put me in the bottom 35% of people who play Call of Duty Warzone. So it's pretty abysmal. Definitely not going pro with those type of numbers. And here's a recent clip of some potato video quality of me playing Valorant recently, me missing all the time. So yeah, I can get better with my aim. So so one day I got the crazy idea after my friends were BMing me to make a robot that actually shoots into games for me. So this is that robot right to my left. So I was able to build this robot just with hobby electronics. And here's a short clip of that robot in action. We're going to be talking about Aim Lab, which is an aim training software that you use basically. And this one to the right is the Great Shot Ultimate. So basically you see how fast you can fast and accurately you can move yourself to click on these blue dots. So what I did was build a robot that can do that for me. So, and that's where I did all the testing for this robot that I had made in mind. So, but it was to get to this point, you guys see on the right, it took a lot of work and a lot of time. So first I'm gonna be how to build this aim hack robot from a hardware design component. The biggest thing I needed here was be able to move the mouse in any direction. So it instantaneously I needed to be able, just like a human does, move to the left, move to the right, move up, down, diagonally. One big thing that I was making this, and after I posted this video on my YouTube, was that a lot of people said use a linear gantry, something like this. But that would have been, I think, a little bit more complicated than the solution I ended up deriving. A little more, definitely more expensive to whip something up like this, and definitely too big to fit on my desk where I was doing most of the robotics development for this. So I decided to build a little robot car that uses Omni wheels. And for people that don't know what Omni wheels are, these are wheels that have rollers on them. So they can only they can drive in one direction and still get friction on the ground, but then they can get moved across in another direction. So if you lay these out in 2 omni wheels on the left and right, 2 omni wheels on top and bottom, you can drive them to simultaneously in pairing to go left, right, up, down, and diagonally. So this is basically, I need this something called hollow knock motion. We're able to go anywhere instantaneously. So, and then from a hardware side, this whole thing was using hobby electronics for the most part. I mean, it's a teensy microcontroller that's taking serial input commands. I had some small micro metal gear motors that I found from Pololu, and I was using low power motor drivers to drive this whole thing around. So it was it took some development to get here, but I mean, at the end, it was a pretty cheap thing to put together. I kind of tried to keep it as simple as possible just to make sure everything works easily. All right, so that was the hardware side of things. So next we're going to talk about like how in the software I'm going to isolate the targets, those blue dots on my screen. So the first thing I needed to do was take a screenshot. So for running this whole software application, the main thing I was doing this in Python. And yeah, I probably wouldn't recommend if you're really trying to build something fast, but Python, the language I was most comfortable with using. So the language I was going to use for this project. So I did screen capturing of the screen. So this was able to get 70 FPS, but we'll talk about more in detail how I like optimized for that and how I built up that solution. Next, I needed to go from RGB to HSV, so red, green, blue color mapping to hue, saturation, value color mapping. And because this is easier to represent a color than in RGB. So when I see, so you can see in this image in the bottom left, so when I see the blue targets in the HSV, it's a lot clearer to kind of distinguish where those things is on the screen. And then after that, I can thresholding based off of like where those targets are. Because as you see, actually the ball in this image is kind of like changes the gradient of color throughout. It went from like this dark blackish blue on the bottom to this very light blue on the top. So in the HSV mapping, it was kind of easy to run the threshold that. So after I do that, I can run a mask and on the blue HSV colors to attract the blue color from the dots. And yeah, so I get very clear distinction of where the targets are on the map. So with this, I mean, you can map out, I can get the centroids of where these 3 dots are on the screen very quickly. And then the next big thing was how to choose which ball to shoot. So I need to figure out which ball to target first. So, you know, I went back to a little bit high school algebra, you know, little distance formula. I know the middle of my screen, let's say if you're 2560 by 1440p, my middle of my screen going to be like 1280 by 720. So that's going to be my midpoint. And then then I can calculate where each ball distance is to that midpoint. And then I chose the simplest method, which is choose which one is the shortest distance. This is, I believe, a good strategy, but I don't know if this is the most optimal way to go about this necessarily. Because like if you're, let me show you video, if you're close to one object, that doesn't necessarily mean you might be moving faster in another direction. So it might actually be faster to go towards a farther ball, but a ball you already have vector velocity unit vector pointing in that direction. But that's not how I did it. I just went for the closest target and it worked pretty well. This video showing that. So this is me just moving my mouse around in the middle of the screen, just pointing. Now I know which one is the closest target at all time. Okay. All right, so the next thing, I'll leave this playing. All right, so next thing, moving the robot to its target. So the last thing, so now I know I have the hardware, I can move the physical mouse around. I know where the targets are. So now the very last thing was just commanding the robot to go to that target. So I couldn't just tell the robot to move to a position because there was a lot of wheel slipping and just other factors. So I use feedback from where the target is on the screen and provide a proportional value of the distance the target is to the screen to where the robot needs to move to. So, and when you do this, you get some oscillation. So I think this video on the right shows like I shoot this target and then there's some overshooting right there, and then you gotta go back on the target. So it's manually tuning how much power I want to give to the robot based on how far the robot is. So that takes a lot of tuning. So, but this early version of the robot, kind of see how it was bad at finding the targets, but and this early version wasn't really constructed well. You can see there's a lot of slop actually in like the middle where I fit the mouse into. So bought a cheap Logitech mouse and just like slapped it in the middle of the robot. So this robot wasn't constructed best, but I mean, it showed that this wild idea I had was actually possible. And that was like the biggest thing I needed to see. All right, so make sure this is looping. So after I knew it was possible, I got into the manual tuning and debugging problems with the code. So to the left is my trials. I tuned this controller that we call a PID controller, that oscillation curve about 80 successful times. A lot of times the robot broke down as I was doing it. So on the right, you can kind of see like the robot progressing from early on when I was tuning the PID to very later on how to get it right. So each one of these red triangles on the left kind of like show like big breakthroughs I made and like how I was going about tuning it. So like, I mean, the very first one was like, I just made the mechanical interface of the robot better. Then went around, I got like 40,000 that I was using PI controller, just using proportional things. But then I also added a derivative term. What does this mean? I added damping. So not only does the ball provide power linearly to how far it is, also like then it maps based off the latch error how much power to provide. So it dampens, it smooths it down when it's going closer to the target. So basically, and then my really big breakthrough, and I don't know why I was dumb and didn't think about this early on in the process, was my control loop was pretty slow originally. It was like going at like 20 FPS. It was like it wasn't updating as fast as it needed to be. So one of the biggest things was going from that 2K resolution I was running at 2560 by 1440p and just like bumping that down to 1280, 720, and then eventually bumping it down to 800 by 600. So the robot was actually updating fast enough to actually do what I needed to do. It wasn't overshooting and then thinking it shot the target when it didn't. So at the end of this video, see here, you got to like 50,000. 50,000 was like, that's when it started beating my score. I usually get around, actually, I've never broken 50,000. I usually get around 40,000 to like 48,000, something like that. So that's when the robot got better than me. So, but then after, all those successful tuning, I finally got a really good performance. So I got this is about a score of 118,000 in AimLab. So this score is kind of better than most shooting game pros from what I saw. Like most pros would get score around 70,000, 100,000. That's like average pros. And like people, like some pros get like a super high score, like upwards of 140,000. But so like this put me in that like really elite high level range. So this is a best. So overall, this score ended up being a top 8,000 out of 6 million tries or something like that. So this puts you in the top 0.1% globally. It ended up having an accuracy of like 89%. And the time to hit the target ended up being 173 milliseconds. So that was pretty cool. So I was pretty happy with the end results of this. I was just kind of happy with like how I had this crazy idea and it came to fruition in the end. So I mean, I'll keep that on loop. Yeah, that was the end of my presentation. That's kind of how I prepped it for only 10 minutes. If you want to see other cool things I do, that's my YouTube on the bottom, YouTube Kamal Carter. So yeah, if you have any questions, thanks again for everybody for setting this up. It's been a really fun event. And yeah, I answer any questions anybody have.
Yeah, I absolutely love this. This is so good. This is something you can't see anywhere else but the Reddit Robotics Showcase, where someone has put this much hard work and talent and like the hardware design and like the neat wiring through to the machine vision and a good explanation of it, and then the maths walkthrough that is all there, and PID tuning, all for the sake of just hitting those little blue balls. I absolutely love it. It's really, really good, and I really do like. Yeah, it's so well executed. It really is something. So you mentioned at the start, obviously, Call of Duty, and low KD rate. So I guess then the next sort of steps are to get this to recognize people, but you have to recognize people in a very elaborate method too. So what, a webcam pointing at the screen with deep learning running on it or something like that? What's next then?
What's next? I actually have already done that. What? Yeah, so I can kind of show that to you. So the big thing is, like, a lot of people had commented when I originally made this. Like, first off, it's great. Like, just take the PCB out the mouse and like put it into one hardware thing and like then move around like that. So, and then after that, you can do some, like you said, you can do some machine learning. You use some object detection algorithm, probably something like YOLO V5, and then you think PID tuning sucks, but then machine learning, training that data to detect a character, whether it be in Call of Duty, Valorant, or whatever shooting game, it will just take a lot of time doing something like that. And then, yeah, after that, you can use some other screen capturing software, or you can use a video card to do it, or point a camera to your thing, just finding targets like that. So, yeah, I actually already made that video, but for this one, I think this was simpler to explain for this showcase. Yeah. So.
Yeah. Have you thought at all about, trying to reduce the weight of the system? So even like moving the PCBs off the actual moving part, maybe even like going so far as to take apart the mouse so that it doesn't even have a shell. It just literally has like an optical sensor and a way to click. What are your thoughts on that?
Yeah, that would definitely be what you would do. Actually, actually, I didn't want to share that robot because that robot seemed like kind of hard, but that's what I kind of did right here. It's like you rebuild the whole mouse. You take the PCB out the mouse, put it inside of this thing. I don't have a screwdriver with me right now, but and then you have a solenoid do the clicking. So yeah, that is the next step. So something like this.
Okay.
But also, yeah, so that took a lot of time, and yeah, I think I'm gonna move on to different things now.
Yeah, I can appreciate. Yeah, there's fun as this, there's other fun things to be doing as well. But yeah, really, really cool project. And I like I really like the execution. One person's asked, said you could use HAR cascade, so cascade machine vision as a technique. That may well work in a video game context where there's less variation. In Valorant, maybe, where there's more consistent lighting variables. Don't know.
Yeah, so I was looking at that too. I had no actually I make sure I don't show anything I'm not supposed to see. Actually I'll actually show that video. But yeah, you can use something like HAR cascades. I don't know anything about it. Like, when I was looking up object detection models, everybody was just saying use YOLO V5. So that's kind of like what I would think is the next step of something like that. So let's do it like this. So this is the other mouse video. Let's show this. So let's say you take the mouse out the PCB, you can make the own hardware for it, and then what you can do, and now I did it in a different game, but you can use that to detect objects like zombies and stuff at unturn or anything like that. So that's pretty much how you would go about doing the next step if you really want to crack this bad boy open and really start cheating. But yeah, also ethically, I don't endorse cheating, so yeah, everybody need to know that. So yeah.
Yeah, of course, this is for entertainment only.
I think yeah, it would be nice to have some kind of like an esports, but just for the bots.
Yeah.
Just to see what the bot
just for the robots, yeah. Like how chess bots just compete against each other, just robots playing against robots. Yeah.
Right. I don't know if we've got any more questions, in which case that is going to be our final presentation. I just checked.
Yeah.
Oh, no, hang on. We do have Calvin has joined.
Yeah,
we weren't
Calvin's
sure if
here.
he was going to make it, but he's made it. Fantastic then.
Sure.
Calvin, I don't know if you're immediately ready. We can happily give you 5 minutes or something like that.
I'm good to go whenever you are. I'm just
Okay,
over
wonderful.
at the in-laws house. So if I drop out, well, I don't have great connections here. So just a heads up there.
Fair enough. We're all about flexibility today.
Well, bear with
Yeah, right.
well, in that case then, Kamal, thank you once again. That was really, really good. That was a lovely novel presentation of the aimbot hack mouse, and really great presentation
cool
alongside it. Hope I will be following to see what you are coming up with in the future.
Yep. Thank you, everybody.
With that, over to Calvin, who is going to be talking about B-bot in real time, which is trajectory optimization, but that's not my forte, so he will explain it better than me.
All right. Well, thank you very much. I will go ahead and share my screen and we'll get started.
All right, we can see your screen.
Excellent. Here we go. My name is Kelvin, and I am with the University of Iowa Cooperative Autonomous Systems Lab, or CAS Lab. And today we're going to talk about B-bot real-time. Now, B-bot real-time is a motion planning algorithm. So first of all, what is motion planning? Well, motion planning is how we get from A to B without crashing. However, there might be other metrics that we might want to optimize for. As we can see up here in this little webcomic from Willow Garage, we can see that the robot trying to get from A to B, it's really not taking an optimal path. So we might want to minimize fuel usage. We could minimize the probability of crashing into pedestrians, or we might want to maximize the coverage of a search area. And of course, there are tons and tons of other metrics that we might want to optimize for. So it is important to develop algorithms that are somewhat agnostic to the metrics that we use. Now, motion planning is widely used. We use it in self-driving cars. It's used on the Ingenuity helicopter that's flown several times on Mars. We can use it for search and rescue, autonomous delivery, and many other possible situations. Now, unfortunately, in real time, there are several challenges for motion planning. We oftentimes have a limited sensing range. So this could be, for example, the limit of a LiDAR sensor. A camera, of course, is not going to be able to see through obstacles. Of course, there are other sensors that just don't give us a full view of the entire environment that we're working in. Also, we're pretty concerned about computation time. Obviously, a trajectory that takes 3 weeks to optimize really isn't going to be useful unless this is a situation of optimizing a trajectory for like a flight path of a rocket. But if we're driving through a busy mall or something, we need to be able to make these computations really quickly. And oftentimes we don't have a really large computer to use. And so we're going to try and get these computations really, really quick that can run on embedded systems like a Raspberry Pi or a Jetson Nano. We also care about deconfliction. Now, this is more for if we have a team of robots, but if we have vehicle number one starting to optimize, it's not going to know what the vehicle two's trajectory looks like until vehicle two finishes. But if vehicle one starts optimizing before vehicle two starts, then vehicle one might end up generating a trajectory that would be in conflict with vehicle two. And then finally, like what I mentioned before, dynamic obstacles. So if we're trying to go through a busy mall, or if we're trying to, for example, drive a self-driving car, we obviously don't want to hit pedestrians or other drivers. So my solution to this problem is the jellyfish search. And it was originally inspired by Mater's octopus search, and you can check out that excellent paper at that link right there. But this is a random sampling approach. Now, in motion planning, there are two really popular ways to solve the underlying optimal control problem. You can do a sampling-based approach or a gradient-based approach. Now, gradient-based approaches take some initial guess and slowly step closer and closer to whatever minimum is in the local area. Unfortunately, there are some mathematical problems there that can result in trajectories not being optimal, and sometimes it can even fail out and be infeasible. On the other hand, random sampling approaches can sometimes be incredibly computationally inefficient because we have to sample such a large space of trajectories. So the jellyfish search solves this problem by solving many simpler problems that have been randomly perturbed. It then assigns costs and feasibility metrics using the Bbot library, which I spoke about last year, and you can also check that out on GitHub through that QR code. So solving the problem of a limited sensing range. Since we're unable to plan for unseen obstacles, we're going to use a safe planning circle. So in this example, let's say that this green dotted line is the maximum limit that the LiDAR sensor on our robot can see. So we're not going to plan anything outside of that perception limit. However, we limit the planning radius a little bit more by this d-stop value. And this d-stop value is just the amount of distance that we would need for the vehicle to go from full speed to a complete stop. And so that just makes sure if there is some kind of obstacle that is just outside of our perception limit, if we need to perform an emergency stop, we're going to be able to stop before the vehicle actually hits the obstacle. Now, in order to handle computation time for the random sampling, we can't really sample uniformly from all possible trajectories because that would be inefficient. So on the right, we can see some potentially good trajectory samples that we might want to use, but in many cases, these trajectory samples would not work. However, both sets of trajectories could end up being sampled from a completely random algorithm. So rather than just completely randomly sampling the entire space, we decide to solve many easier problems that are all randomly perturbed in their own right. Now, we use calculus of variations and an LQR controller in order to solve that, but I'm not going to get into the math here. But I will be publishing a paper, so eventually, if you're interested, you can check our lab out, and I'll have a link to our lab at the end of this presentation. But then finally, once we have solved those many simpler problems, we have a large family of trajectories, which we then use the Bbot library to efficiently check both for feasibility, and then we also assign costs to all of those trajectories. And then finally, we pick the trajectory with the best cost that is also feasible. Now, deconfliction is what I was mentioning before. How do we avoid multiple vehicles crashing into each other? Well, in order to do this, we can check and recheck for collision. So in this example, vehicle 1 starts optimizing. Now, before vehicle 1 finishes generating its trajectory, vehicle 2 starts optimizing its own trajectory. Now, vehicle 2 ends up completing its trajectory search faster than vehicle 1. So if we did not check for collisions, vehicle 1 would not be aware of vehicle 2's trajectory, and as a result, vehicle 2 might end up crashing into vehicle 1. So we first check for collisions before we pick the trajectory that we want to use from vehicle 1's optimization scheme. And in that check, we're going to be able to figure out that yes, vehicle 2 ended up optimizing its own trajectory. And so then that means vehicle 1 needs to go back and re-optimize. And then finally, this last little check is just a check to see if anyone else started in trajectory optimization right before they finished up the checking for collision. And so this should guarantee that we never have two vehicles that generate trajectories that are in conflict with each other. Now, finally, dynamic obstacles, we're going to want to deal with environments where we have people moving or cars moving or any other obstacles moving around. And in order to solve this problem, we choose to replan trajectories periodically or when a new obstacle is encountered. Now, this requires fast computation, which can be solved using the things that we spoke about before. So here's an example. We can see that the vehicle is in its safe planning radius right here, which is the perception limit. We have an obstacle here that is denoted as the triangle. And then this green rectangle shows us the map that the robot is aware of. The red rectangle is the entire environment that the robot is in. And so we can see that this orange obstacle over here is not on the map. And so the robot is not aware of it. And then we have the goal position denoted by the star. So what the robot's going to do is first it's going to shoot out just straight lines to the goal. So it'll shoot out a straight line over here to the side of this obstacle. But then we can see that the straight line goes directly through this obstacle out here because this obstacle is not in the known map of the robot. So the robot creates an optimal trajectory in order to get the goal while also avoiding this obstacle. However, at this point, it's not aware of this dynamic obstacle that could collide with it because that obstacle is not within the safe planning radius. But now, as the robot moves, we can see that the dynamic obstacle's trajectory is now in our safe planning radius. And so then the robot will replan. It now has a new straight line guess directly to the goal because it's avoiding this obstacle over here. And we can see the new resulting trajectory that avoids the dynamic obstacle and avoids the known static obstacles on the map. So here is an example of a simulation running using the jellyfish search. When the balls turn red, that means that the optimizer is aware of the obstacle, but when they're blue, it's not aware of them. And that blue path that the vehicle is following is the best cost trajectory, whereas the other green trajectories are some of the other better trajectories that were generated. And we can see that the vehicle easily is able to travel from one side to the other in real time while avoiding collisions. So that is what I have got for you folks. You can check out our Bbot library at GitHub, and you can also check out the University of Iowa CAS Lab at venanciochikela.com. And if you have any questions, feel free to shoot them to my University of Iowa email. But I'm open to questions now. Thanks.
Okay, I'll definitely let Michael take the lead on this one. This is not my forte.
Absolutely. Yeah. Well, first of all, thank you so much for your presentation. This is really fascinating. We have a question from the YouTube stream, which is, how would the robot infer the path of a dynamic obstacle?
Oftentimes, inferring the path of a dynamic obstacle is done by taking a first or second order approximation. So we're able to replan trajectories pretty quickly in the sense of, less than a second. And so oftentimes a dynamic obstacle is easily predicted as just a straight line with its current heading and its current speed. Now, there are other algorithms out there that can get a little bit fancier. For example, you can use machine learning in order to infer what a pedestrian might do. And this is really popular in the field of self-driving cars. But it does kind of depend on just what situation you're going to be in and what obstacles you're expecting. So yeah, normally I would start off with that first order approximation, just take the current speed and direction and just integrate that out to a specified time step. So maybe 1 or 2 seconds out.
Yeah, cool. I guess a question that I would have is, so most of my work is focused on stuff like industrial robotics, linked arms and stuff like that. And I'm just curious, how would a motion planning algorithm like the one you described work in the configuration space of like a 6 degree of freedom robot arm or something like that? Do you think this is still applicable, or do you think this is much more applicable to something like a Roomba or a car or something?
So this actually is very applicable to your field as well. Now, I personally have not written algorithms for that because we focus on mobile robots in my lab. However, what you would do is it comes down to how you formulate the optimization problem. And so I'm sure you've dealt with, solving like an optimal control problem subject to the dynamic constraints. Well, you'd have kinematic and dynamic constraints. So x dot is equal to f of x. And so using the Bbot library, we're able to solve problems exactly like that, except rather than using, for example, if you're working with like with Lagrange polynomials, we're using the properties of Bernstein polynomials, which have some really nice properties to them. So for example, if you're looking for like the maximum speed of a specific link, rather than needing to discretize the polynomial and check, we can actually check in continuous time, because a Bernstein polynomial is going to be enclosed by the convex hull that is defined by its control points. So that means that in full continuous time, you can still guarantee that you're not going to like hit a maximum speed or something like that.
Okay, yeah, it's very interesting. I'll look into that. Do you have any plans on releasing this as an open source package consumable through RRS or any current popular framework?
Yep. So I work with RRS quite a bit in my lab. I'm currently working on getting Bbot written in C++, and then that will go out as a RRS package. And then similarly, so will Bbot real-time. So you can find Bbot real-time if you go through our GitHub links, but I'm just not putting the link in here just because it's not up to my standards quite yet. But you should be able to find Bbot just through the CAS Lab GitHub organization.
Great. Okay. Well, that kind of does it for my
So,
question.
Can I ask a question? And as I've hinted at, so I'm aware that this is being applied for autonomous drones. If you were to apply it to, vehicle, if some of the other robots we've seen here, whether it's the small little robot with 2 Raspberry Pis and an NE5, or going back a bit further, the tour guide robot at the University of Lincoln, and they were talking about the challenges of navigation there with people and things like that. How well would this theoretically apply? Is this something where you really could, drop it in, or are you then looking at months of work to tailor it for a different domain?
Yeah. So this framework is actually designed to be very, very general. So this could even apply to fields outside of robotics. For example, there in the medical field, you can do like optimal dosages for medicine. They have like real-time medicine where you'll be hooked up to an IV, and then a machine will be sensing other biometric features that are going on, and then it will it uses a control law in order to give you like medicine at an optimal rate. Similarly, if you were trying to like play the stock exchange or something. So this framework is wildly general, but of course with generality does come a lot of work when you want to implement it specifically for what you're looking for. So I've of course gotten this working with a plethora of different mobile robots. We're doing a search and rescue marine environment right now. So I've got an underwater vehicle, a surface vehicle, and a drone that are all going to be running bbot on them. But for example, getting into the robotic arms and other things like that, that's where you'll have to start defining some of your own cost functions. So it comes down to, can you define your cost functions as Bernstein polynomials? And if you can do that, then you'll be able to solve your problems very quickly and efficiently. And so in my bbot paper, we give tons of examples of how you might do that and what properties of Bernstein polynomials you might want to use. And then, of course, anything that works with bbot will directly apply to bbot real-time as well.
Okay, and I'm looking through the GitHub whilst processing this. Does that mean there are then examples that you can use to reference, you know, here's an example of bbot with a quadruped, bbot with the search and rescue domain, you know, is that something where you can then use that and, you know, have it running on something in Gazebo or simulator then?
Yep. So the examples that I have on GitHub for bbot are all the examples that we use to generate the plots in our paper. And so those are going to be just pure Python examples, but it should be really straightforward to just wrap those within ROS. Here with my last year of my PhD is kind of where I'm starting to wrap all this together into nice packages. So that's why I'm saying, like, yeah, we've got all the research done, but now I want to get some of the more implementation side of things pushed out and ready for people to use.
So I'm saying, would it be valuable to have ROS packages or a ROS package of parameter files for those different scenarios then of a quadruped, of a quadrocopter, of a four-wheel mobile robot, those kinds of things, so then people have an easier starting point of how to apply it to their case?
Yeah, yep, and that is actually part of the plan moving forward. Is I want to have so rather than just like Python examples like what we've got now, I do want to set it up where, you know, you can just ROS launch, and we'll probably do several of the most popular robots. So we'll probably get a quadruped there. Of course, we'll get a drone and probably a turtle bot. And then just because we're doing this marine search and rescue, we'll probably also have a surface vehicle. I really like the Robot X, the VRX simulator. So I'll probably use something with that. And then the biggest challenge I would say would be the underwater vehicle, just because it seems like it's still an area of research for people getting underwater vehicles working properly within Gazebo.
Aren't getting underwater vehicles working, period?
Yes, you are correct there.
Simulations, swimming pools, oceans, doesn't matter. It's a tricky challenge.
You are correct, yeah.
We have one more question, a really great question from the YouTube stream, which is, you know, how I guess computationally intensive is this algorithm? You know, would you be able to deploy this on an edge compute or an embedded system, or would it need to run on like a hardware accelerated server and then relay that information downstream?
Yeah, that's an excellent question. This has been designed to work on a Raspberry Pi. And so, yeah, it'll compute within a second or so on a Raspberry Pi. And there are other optimizations that I still want to make because, as I stated before, there are some things that are a little bit more general where I could go ahead and take advantage of, you know, certain aspects of a specific problem. But yeah, so far this has been shown to run in real time on, you know, some of these more edge type embedded systems.
And are you still running it in Python and it's finishing in under a second?
Nope, I did actually run that on in ROS, but yeah, like it's in Python in ROS.
Yeah.
And then I use the Numba package in order to get compiled feeds out of Python. And then, of course, if I can't use Numba, I'll still try and use NumPy really heavily to just make up for, you know, their vectorized math and the parallel stuff that they can do with, you know, like the large matrix operations and whatnot.
Makes a lot of sense.
Okay. Yeah, fantastic. I guess then is if you gave us a presentation last year, this year, and next year is then going to be showing the final results then, hopefully. And,
I most certainly hope so, yeah.
And I for one would be very keen to see those ROS packages when they're ready for the world. Don't be afraid to you know, wait until they're perfect, because they never will be.
Yeah, right.
if that isn't the pot calling the kettle black.
Yeah.
But yeah, because that is, I can see the value. Yeah, it's a very robust motion planning model that can handle a lot of different scenarios. Something that then, there's examples as well that people can easily set up a simulation and then apply it to their vehicle in their domain, can become a very useful, powerful tool. Exciting.
Yeah. Well, thank you very much. I had a blast doing this presentation, and I really do want to get this out into the community. I really look forward to seeing what people can do with Bebot.
I think we can we should have a think of ourselves, Michael, about how we can promote some of the open source tools and things like, and projects that, you know, other people can replicate from this year's showcase, so that there's kind of a single page for that. Wonderful. Right. Well, that is the end of the session, the presentation, and therefore the first day of the showcase. I will make myself the spotlight. So thank you very much, everyone who has been watching, whether you've just been stopping in for 5 minutes or sitting attentively throughout the entire day. I hope you've enjoyed it and hope maybe learned a few things or been inspired in some way. And we will see you tomorrow for the second day, starting 10 a.m. Eastern Daylight Time, 3 p.m. British Standard Time. Sorry, there's a comment there that says, "Damn it, just missed it." I'm sorry. So starting at 10 a.m. Eastern Daylight tomorrow, that's 3 p.m. British Standard Time, will be our category 3 bio-inspired robots, where we've got lots of different quadrupeds and a couple of humanoid robots as well. Very exciting to look forward to, as well as a keynote presentation on snake robot arms inside jet engines and for surgical applications. And then finally, our last category, human-robot interaction, with the very esteemed Dr. Ruth Ehlers of the National Robotics, who's got a very illustrious career of research in the field of social robots and human-robot interaction. And then all kinds of different presentations there in that last one, from interactive robot art through to telepresence gloves and a general-purpose humanoid. So there'll be lots to look forward to tomorrow, and we hope to see you then.
Should be a wonderful day.
Wonderful. Thank you very much. We will leave it there and see you tomorrow.
Thanks.
See you tomorrow.
Cool, we're done.